the most about this is that it was discovered in Australia on February 28th, which I guess was February 29th over there. And then the comments are awesome. Like somebody's like, we better fix this now so it works in 2028. And somebody else is like, oh, the Americans will do it tomorrow. So if this doesn't get fixed by 2028, I'm okay with that. But my least favorite bug is I think it's still open. You should close the issue. I think so. Yeah. Yeah. And my least favorite bug, it might be a wasp. It might be anything that goes wrong in Dask. I've been stung by both many times. The agenda for the next 3 hours. Okay, so we're in the welcome talk. There'll be some talks on testing and software engineering tools. We have one talk that dives into software like project details, updating CAM and POP2 to do some research. Then Alper will introduce us to a CSM GUI. And after lunch, we have 3 remote talks, IO infrastructure, and data assimilation, a talk on lossy compression, and a couple talks on diagnostics. In table form, it looks like this. I don't know why I didn't print this out and hand it out to people, but here it is. For tomorrow at the very end of the workshop, there'll be the hour-long discussion. And so if you want to ask a question in Slido, you can use that barcode. I've got this on my phone, so just find me and I can show you the barcode and you can get the link that way. There is not going to be a software engineering specific social gathering. Sometimes there's a dinner on the night after the workshop or after the working group talks. But tonight there's a social thing for the whole workshop at Sanitas. So we're just going to go to that instead. If you picked up the forum with like the directions on how to get there, Google Maps wants you to walk south of the place and then jump over train tracks. Please do not cross the train tracks. There's a walking path along Pearl Parkway that Google Maps doesn't know about. And so just walk down foothills on a path, cross Pearl at the light. I think if you ask for biking directions, it wants you to cross like in the middle of Pearl Parkway at an uncontrolled intersection. Just cross at the light, don't get hit by a car. The beer is much better when you're not in a hospital. Some CSM specific updates. So we've had 2 new releases in the last year, 2.15 and 2.22, both added support for Diretto. Also, GitHub dropped their support for subversion hooks into Git repositories. And it turns out that there's a thing called sparse Git checkouts that basically give us what we want from the subversion hooks anyway. So managed externals works in 2.15 and 2.22. It doesn't work in 2.14 or 2.21. A reminder about our support policy. So we have a production release that's 2.15. That'll be supported until a year after the next production release, which will probably be 3.1. It's like the big CMIP scientifically vetted releases. We have development releases. So 2.2 was our last official release. So we're obligated to support it. It's also 4 years old and it doesn't look anything like the current development tags. So I think something on the CSEG side in the works is to update the release policy so we don't have to support a 4-year-old release that has no like scientific value. But for now, we'll support it until 3.0. On the infrastructure side of CSM, like I mentioned, we now support Diretto and we dropped Cheyenne. So if the person who bought Cheyenne is listening, I'm sorry, you can't run CSM on it anymore. We updated the SMF library from 8.5 to 8.6, which adds some basic support for GPUs, some accelerated device management in the NVIDIA compiler support. And it improves the vector regridding for more accurate results, especially in the polar region. There's more infrastructure in place for testing via GitHub Actions. So we're taking advantage of the GitHub virtual machine for testing pull requests before they even get pulled in. We forked FMS so that we don't have to use an old version of the NOAA code with a couple source mods. This is just easier for CAM and Mom6 to share code while keeping up to date with the GFDL updates. You'll hear, I think the second talk will be, or the third talk at 11:30. We've removed managed externals. We're with all the components in Git, we don't need to support subversion checkouts. We don't need our own tool. We can extend the Git submodules. And we're about to tag 3.0 beta 01. So we're like officially entering the 3.0 development, which is exciting. On the component side, we've deprecated the MCT-based coupler. For the actual 3.0 release, coupler 7 won't be in the code. It'll only be the new OPSI-based CMEPS mediator. We've removed POP2, so MOM6 will be the only active ocean component. We've dropped support for CES5 and an older WaveWatch 3. So now you have to use CES6 and a confusingly named WaveWatch 3 that's newer than the WaveWatch 3 we don't use. CMAPS now supports multiple ice sheets in the glacier component, and there's a data glacier model in CDEPS. CAM has also done some GPU focused work on the radiation scheme and cloud microphysics, and they fixed this longstanding issue with the time coordinate and history files. So for average files, CAM will now use the midpoint of the averaging interval instead of the endpoint as its timestamp. And CEIS did the same thing. MOM6 has land block illumination, so it runs 25% faster because it's just the grid is smaller. CTSM added some tools to create service data sets in parallel while the older tools were serial. Fates added a seed dispersal module, which is the first intergrid cell communication for the model. And then there's just lots of process improvements, and I think we'll hear about some of this from Eric. And then there's the simple land interface model and a new river runoff model, Misurat. The proposed timeline for the 3.0 release. So we're in the middle of June. There'll be a science freeze tentatively planned, well, maybe firmly planned for July 31st. And then a period of tuning and coming up with the final forcings for the model. And then a period of testing and documentation and actually running simulations. And then I put this in April. I think Dave's slide yesterday said somewhere in the April to June timeframe will be the actual release of both the code and the simulations. So with that, I'll hand it off to Ligia for some updates from NOAA.
All right. Good morning, everybody. I just have this one slide. So I am the co-chair and I'm representing NOAA. I'm from Global Systems Laboratory here in the Boulder area. And I think one of the reasons to have external co-chairs is just to help cross-pollinate activities that are happening here at NCAR with those that are happening at NOAA. So hopefully we can do a little bit of that. So at NOAA, we've mostly been transitioning now to the Unified Forecast System or UFS, and that is also a community model, just like CESM. So that's one of the points of intersection with this community here. The UFS is supported by an organization called EPIC, Earth Prediction Innovation Center, which you may have heard of. They are the ones doing the UFS code releases and support to the user community. The UFS spans a number of apps or applications, ranging from short-range weather, which is scales from hours and even sub-kilometer to days and a few kilometers. We have applications specific for certain meteorological phenomena like hurricane prediction, medium range weather, which is applications on the order, say now we're running 13 kilometers, global weather, coupled, just like global forecast system, and then going all the way to subseasonal, seasonal, and also applications in air quality and coastal. So it's pretty diverse set of things we're trying to do with this model. And to do that, the model has the capability of running in coupled mode, global, but also can run in coupled limited area. And for the atmospheric model, we use the FE3 dynamical core coupled with the common community physics package for physics. And then we use a number of other components that are very similar. So there's a lot of overlap to what is used in the CESM, such as MOM6, CEIS, WaveWatch. We have different land surface models like RUC, NOAA, NOMP, and also different modules for atmospheric composition representation like GoCart, CMAC, and others. In addition to what I mentioned before, other infrastructure connections with CSM include that we also use CMAPs, the mediator, CDAPs, the data models, ESMF for a lot of the regreading and coupling, FMS, that's part of the FV3 dynamical core and MOM6, etc. We've had connections with CSM in workflow because our first release of UFS was done with the SEAM workflow, but we have since started looking at other solutions. And then we also still use managed externals, but we're looking into phasing out now that CSM is also moving in that direction. And another upcoming connection is related to the MPAS atmosphere dynamical core. That is one of the dynamical cores available with CSM, and we are looking into implementing this dynamical core into the UFS with an initial goal to use it for very high resolution applications like 3 kilometers, but with the possibility of expanding, in the future for other UFS configurations. So just want to point out there's lots of points of connection, both in the software engineering and infrastructure, of course, that, enables collaboration in the science. NOAA and NCAR have a current memorandum of, I think it's agreement or understanding, which says that they will collaborate on infrastructure pieces, so that relates to SEMA on this NCAR side and the UFS and the NOAA side. That memorandum is now getting to its expiration date, so there will be a renewal. So this will be an opportunity to continue discussing where we want to intersect. So with that, thank you, and I'll pass it back to Mike. You may want to say something about this pointer.
Yeah, so two things for the speakers. The ones in the room, I'll give you a 2-minute warning at 10 minutes, and then my timer will go off when it's time to wrap up, and we'll have time for questions. For the remote, there's a big circle that goes forward, a smaller circle that goes back, and the top circle gives you a little pointer on the screen. For remote speakers, if you could stay on at the end of this first session, just so we can test that you can share your screen, and if you need to log out of Zoom and log back in, maybe you can do that during lunch instead of right before your talk. So with that, I think Eric is the first speaker.
Thank you. Eric Kluzik, he, him, his. I am a software engineer and work on the land model. And let's see, forward outline. So this is what I'm going to talk about today. Automation with continuous integration, continuous development. I guess I didn't give the name of my talk. Implementing continuous integration, continuous deployment. Philosophy for CTSM, the tale of bit for bit dev. Okay. So CI/CD in software engineering has kind of become equivalent to automation and automated testing and things like that. But there's other parts to it. And it's not that I disagree that automated testing is something that we should be doing. It is something we should be doing, and it's something I'd really want to get more knowledge about, and we can start applying it to our models. So, but that's not what I'm talking about today. So originally it was a concept on how to build software, and specifically and mostly what I'm going to concentrate on today is the continuous integration part, which means that you're integrating to get your software together when your team that's working on the software often. And I'm going to talk about that and how we had adopted some practices that help move us toward the philosophy of CI/CD. Okay. The main one is our new bit for bit dev branch that uses a Git flow workflow, which was a team effort in figuring this out. And I'll go through a little bit of the history of that effort. And another practice is our near-term priorities project board, where we're using a GitHub team project board, and we're figuring out how to use that, and that's been helpful. Both been positive. The process in and of itself was a team building exercise, so I think it was worth it just for that. It also brought our team to have ownership of our process. Because when we decide on what the process should be and everybody has buy-in, you're going to try to make sure you follow the process. And it provides a mechanism that we can tweak the process as needed, which is really great. So again, automation with CI/CD is awesome, something we will and need to do more of. And, you know, I have some machines there because using machines are something that humans do, and having things that are automated and just automatically happen is really a great way to go. So I'm not really going to go through everything here. But you know, automated testing means we're adopting a software engineering industry best practice. It allows us to leverage the work we do. So you put in a little bit of work and you get a bunch of really good benefits. So do things faster, catch problems sooner, standardize this process, etc. So again, I'm not talking about that, but a little bit of history of this continuous integration term. It was coined back in 1984. Kent Beck popularized it in 1987 with this new idea, which is one of the first agile software development methodologies, X programming. And then in 2006, Martin Fallow had an article about continuous integration that he's actually updated to this year. And so the thing that I concentrate, so if you Google about CI/CD, you're going to see a bunch of our articles about automation and automated testing and automated builds and all that. So a definition that kind of works now is you commit to the same branch sub-daily, and which invokes automated testing. Okay, and I'm going to concentrate on the part. Let's see if I can do the fancy little thing. I'm going to concentrate on the part that's highlighted, commit to same branch sub-daily, which invokes automated testing. Okay, so this is Kent Beck's book on extreme programming. And funny story is I got excited about this book. I saw it in the bookstore because it says embrace change. And CSM, we've been using the same code base for decades. And so we're constantly changing that code base. And so I thought this would be a good disciplined software engineering practice that we could apply to how we actually are building our software. I gave a talk on this that was kind of immediately died. Unfortunately, because, you know, we actually at that time, just NCAR wasn't ready for thinking about change. But that's really always affected me, that there's some practices that we can apply, that we can do things better. So philosophy goals for CTSM. We want to have smaller PRs and tags, commits more often, fix little problems quicker, integrating together on a shared branch more often. And here's the definition of CI by John Stevens. Is a little article I give at the end about this. Continuous integration is a software engineering practice where members of a team integrate their work with increasing frequency. In keeping with CI practice, teams strive to integrate at least daily and even hourly, approaching integration that occurs continuously. So that's the lofty goal. And that's not something we're going to get in CSM for a variety of reasons, which I maybe we'll touch on. So the main one that we did in CTSM is our new bit for bit dev branch, which is using a Git flow workflow. So currently, when I look at my practice, I work on tags for about a month, and then you know, they come in, and the tags come in from the group about weekly for CTSM. And again, you know, the individuals are probably working on a month or more to bring it in. And a practice that I've done, especially because going way back, it was like Bill and I were the only ones that were putting stuff into CTSM. And so if I had some little miscellaneous thing that I think needed to happen, I would just add it to the latest thing I'm working on, which I'll talk about in a second. So there's some pain points with that, is that larger tags make it hard to review, right? Adding things can be problematic. So I've had a practice of I add little things. And so what's happened to me before is I add something, I think it's going to be really easy to add, and then I have problems with it. And then the problem is it's stuck in this other development, and I feel like I have to get it fixed before I can move on. And so that can be problematic. And it also makes things bigger too, right? So bigger tag means there's more integration updates, problems, and conflicts with other work. And the tag queuing slows down development. So some of the time, like I said, we're working on things tags come in about a week. And so a lot of times, there's not a tag that you're waiting on another, but sometimes there is. Sometimes there's a queue process, and that means, I'm not gonna bring my tag in immediately. Oh, whoops, let me go back. I'm not gonna bring my tag in. I'm not gonna do the full final testing for my tag until it's my turn in the queue. So that kind of slows down the development process, the queuing aspect of it. It's a bottleneck. Whoops, go forward. Another thing that's been a disincentive to making small tags is that, you have to update the change log, need to create baselines. So it just disincentivizes adding something small to a new tag. So, they're new. Okay. So still bigger answer changing things still go to master. But miscellaneous things, like I was talking about there, and quick fixes can go to the bit for bit dev branch. Obviously it has to be bit for bit dev or bit for bit. And then it's merged to master every 2 weeks. It's kind of just a turn quick thing. It's easy to review those small changes that are in bit for bit dev, and so that the review process can happen quicker. Small PRs go in without new baselines in the change log. Bit for bit dev is updated for the dev group more often, so it's closer to continuous integration. And we're still testing using our test list. 2 minutes. Okay. Eliminate tag bottleneck for simple changes. This was a team effort. So here's the team history. So Adriana says we should look into the Git flow workflow. And then she kept saying that, which is good on her. It's good on her that she kept saying that. I say infinity. I don't know how many times she did, but I realized after a while we should start listening to Adriana. Okay, and that was in October. And then Adriana and I started on a document, and I kind of envisioned that we would just say this is great and we'll start doing it. But then we need the team to get buy-in. And so we started working on the document and the process and improving it and getting buy-in from everybody and really making sure it was going to work. And that took some time, but it was really worthwhile. And so if nothing else, get with your team and talk about your process and talk about how to improve it. So some results we've seen, there was a fix for Run Neon that went in a matter of hours instead of weeks in a previous example. 24 PRs have come in under six tags on master. The process is easy. It's turn the crank. We take turns and it's much easier to code review. Oops, I keep doing the wrong button. Important takeaways from this. So working on software process is critically important. When people start educating them what is currently done, and later you listen to them on how to improve. Listen to everyone in your team, especially when you think you disagree. Okay. And I asked myself, did I not listen to Adriana because of gender, age, experience bias? And I need to keep thinking about that because sometimes those things just happen. And so it's good to, think about it for yourself if you're having a bias show up. Everyone contributes to the process, builds ownership, buy-in, and personal commitment to the process, builds in a way to continuously improve, get everyone thinking about pain points and how to reduce them, get everyone working the same way, and help spinning up new people in the process. Listen to the team. Another thing that I'm going to gloss over, near-term priorities, GitHub board. So there's some problems. Estimates are hard. And we haven't, making bad estimates is demoralizing. For CSM beta 17, I kept saying that it's going to be done in a week for about a month, and it feels bad to me. It feels bad to everybody else. But we're continually being asked to make estimates, and we need to do it for planning and coordinate work. So prioritization is difficult. Working on too many things at once, nothing gets done. So long-term planning is too difficult to have a handle on. And so some solutions, let's use some estimation methods from the software industry. And the important point is that average of your estimates over time, if they are close to reality, that means they're useful. Forget about long-term stuff. Constantly assess prioritization. Practice making estimates for near-term goals, track and assess them afterwards to improve over time. And so we're using a GitHub team planning template. Okay. And I'm going to just skip that. So this is what it looks like for a current planning. And so there's, a bunch of stuff in progress. Maybe something that's stalled, a few things that are done, and then, there might be some things in the to-do. And then if you look at future sprint, there might be some things that are in progress. There's some to-do, nothing's done or stalled. And takeaways, think about software engineering process for your teams. Work together to develop and improve your process. Listen carefully to all voices. Try new practices and iterate on them. Develop practices that address these: prioritization, planning for short cycles, working on the current cycle, analysis of the previous cycle. Keep redoing above on short cycles. And so there's some references. So when you get access to this, you can look those up. But there we go.
Can you good talk? Can you just talk more about the change log? Because I think you made a mention of you don't do change logs for bit dev, but do for main or master. Yeah, I guess just what's that process?
Yes, exactly. So what we do so we still have PRs to bit for bit dev. And what happens is that there's that 2-week cycle where there's a dev merger that's going to take what's on bit for bit dev and merge it to main. And when they do that, they make a change log that has the summary of everything that was put in. So we still have the change log, which has been so important for everything we do. But it's not something you have to update for each little tiny PR. Yeah. Cool.
Okay, so Jim Edwards is our next speaker, the distinguished Jim Edwards, official now.
Yeah. I had for yesterday's talk, I had all these speaker notes, and I got up to the podium and I realized the speaker notes weren't there. So I missed a lot of things I was going to say, and one of the things was to make a joke about the talk that I was giving was not going to be a dry technical talk about some boring software that nobody wanted to hear. I'll save that for tomorrow in the software engineering group. So So why is my picture up there? I want to, okay. Oh, that's why, because I'm sharing that. Is that the right screen? No, that's not it. Oh, can I share my screen? I am. Let me try again. Where am I? Is it up online? Okay. We just can't see it in here? You might think. There we go. Okay. So I'm going to talk about a new tool, Get FlexiMod, that we're going to use in CSM3 for managing the code distribution of the various GitHub repositories that comprise CESM. In the how do I advance the slide? There it goes. Okay. So I'll start with, well, what's wrong with the current tool we're using, Manage Externals, and why do we need to replace it? And then why can't we just use Git? Why do we need to develop a new tool? And then I'll talk about adding to the Git modules file, the sparse checkout feature, and backward compatibility that I know some of our partners are concerned about. And I went the wrong way. So Manage Externals was created to support both Git and Subversion repositories. We no longer have any, I said suppositories? Repositories. We no longer have any Subversion repositories. So so we had functionality there that we didn't need. And then more recently, GitHub ended their support for Subversion API that we had been using for sparse checkout and Git. So there was a lot of functionality in Managed Externals that we didn't need any longer. The original developer of Managed Externals had left NCAR quite a while ago, and that left support up to me because nobody else wanted to do it. So back in December during the Christmas break, everybody was out on holiday, and I spent a week writing a new tool to replace Get FlexiMod, or to replace Manage Externals. And then I spent a while convincing everybody that we needed to use it. So I don't know if you can see that. That's the help message from Get FlexiMod. I'm sorry, the font is a little small in it, but it's got 3 simple commands. There's update, status, and test. And that's it. And then you can specify a particular submodule that you want to apply to. You can have optional submodules that you don't check out by default. You can force overrides if if it tells you I'm not going to do this because you've got some local change in your repository, you can force it to just ignore that and overwrite it. And then there's a couple of debug and verbose options there. So why not just use Git? Well, it's kind of an ego problem, really. We have CESM, which we want to distribute with all the component models, but the component models themselves want to be distributions. So CAM wants to be its own distribution, and CTSM wants to be its own distribution. And so we had to kind of figure out how to solve this problem where everybody wanted to be on top. And so what Get FlexiMod does is it handles submodules, but it gives you a little more flexibility about which submodules you're going to check out at any given time. And so these are the submodules of CESM, just looking at the top level. And then many of these, for example, CAM and CTSM have their own submodules underneath, right? So if we look at, I picked CTSM, it's a little shorter. If we look at the submodules of CTSM as a top level repository, it has all these things that are needed to run a CTSM experiment. But if CTSM is a submodule of CESM, the only thing you need here is fates. Go. Oh, come on. There it is. Okay. So as I said, Get FlexiMod is an extension of Get submodules. It also uses the Get sparse checkout functionality, which is still within Get. It's still a experimental feature. It's not guaranteed to be. It's not an official supported aspect of Get. But Get submodule uses a Get modules file, which is just a basic configure file. And so you can add variables to it without interfering with what Get submodule wants to use in the file. The difficulty with that is that you don't want to add variables whose names are likely to be overwritten by a future implementation by Get. So I intentionally chose I chose this FX prefix just to kind of assure that Get wouldn't choose a similar name. And then one thing I'll point out here is this FX do not use URL. I originally called it FX URL, but then people tended to change that when they wanted to change the URL they were referring to, and that wasn't the purpose of that variable. So I tried to make it clear, but if somebody has a better name for that, what's that? That's just for testing. Yeah. So what that variable does is you can use GitHub workflows. Using GitHub workflows, you can run a test to make sure that the submodules you're bringing in are from the official repository and not from somebody's personal fork. And it just gives you a added level of testing that you can use with GitHub workflows. And backward, am I already at backward compatibility? Wow. Okay. So we have a number of other agencies such as NOAA's UFS, the NOR ESM. I just learned yesterday, I tuned in yesterday afternoon to the Ocean Model Working Group, and I learned about the Access model in Australia. There's a growing list of modeling agencies using CESM as a base for their modeling efforts, which is really exciting. I'm happy to see that. But there has been some concern that our change from managed externals to Get FlexiMod was going to cause some problems for those agencies. And I want to assure you that I don't think it will. It's a pretty easy transition. For one thing, if you don't have the ego problems that we have in CESM, you can just use Get submodules. You don't need to use the Get FlexiMod tool. And if you want to continue to use managed externals, but you want to import a new CESM component that uses the Get FlexiMod tool, you can use this, what I'm showing here on the right is you can just say from submodule equals true in your externals.config instead of having the URL and tag, and that'll make it that'll make your Git FlexiMod component, your Git FlexiMod enabled component compatible with your managed externals top level software. And then, yeah, the reason I got my computer out and did this separately is because I wanted to try to do a live demo. If we have time, do we have time? Okay, I have to stop sharing and then I have to share again, I guess. That work? Yeah. Okay. So, I have something checked out here. And then we also decided to put Git FlexiMod into the component models and distribute it with CSM. That's not necessary at all. You can get FlexiMod from pip and use it as an external tool. Install it yourself, but it is there for convenience. And the first thing you'll notice is that if you don't have the right level of Python, it gives you a nice, easy to understand error message. But I can't remember the names of the modules on Izume, so I have to, oh wait. I have to ask it. It's Lang Python 3.11. That one works. And then we can do, for example, status. This tells you all the submodules of CTSM and what their current status is. You can see that in this case, Fates is checked out, but none of the other top level components are checked out. So we can check one out, for example, CCS. Now, and if we run status again, we should see that CCS config is checked out. Yeah, and it tells you a tag. The combination of Git FlexiMod and Git submodule, it overdefines the tag that you're checking out, because Git submodule has a tag that's stored in the Git repository, and Git FlexiMod is storing a tag in the .git modules file. So you have to have a mechanism to make sure that those stay aligned. This is telling you, that your tags are either aligned, or if you get them offset, it'll tell you that, they're out of alignment. You need to fix something. And also in the Git workflow testing that we provide a mechanism for, it'll tell you if things are out of line and make you line them up before you check something into a master repo. I'll be done. Sure.
Do we have any questions? We're going back to this. That road. That's upside down. Here you go.
Should this be? Okay, cool. All right, so hey everyone, my name is Josh Coop. I'm a postdoc at CU Boulder, and I'm going to be sharing some work on incorporating ultraviolet radiation inhibition of phytoplankton in CSM, specifically marble, for many use cases. All right, so I'll first lay out some motivations and lay out the objective for all of this. And we're trying to develop a tool that's capable of simulating UV radiation inhibition of phytoplankton for all of these use cases. So the primary one is for an asteroid impact, specifically the Chicxulub asteroid impact at the KPG boundary, which likely caused a mass extinction event. And this asteroid would have injected soot, dust, water vapor, NOx, and ozone depleting halogens into the stratosphere, likely depleting stratospheric ozone and letting in ultraviolet radiation. And we want to simulate this and how this affects phytoplankton. This tool could be used for nuclear war. So soot injections from burning cities and a large scale global nuclear war could inject soot into the upper atmosphere, NOx. This could be used for volcanic eruptions where sulfate-based aerosols could affect ozone as well, or even water vapor. And then we're also looking towards using this for stratospheric aerosol injection based climate mitigation scenarios, or even there's been research that large-scale wildfires and their organics and black carbon, as well as NOx entering the stratosphere, could have effects on stratospheric ozone in the future. And so this project is mostly funded by, it's an NSF grant looking at the asteroid impact. There's also some funding for the nuclear war scenario. So getting into the methods quickly, we're using, we're calling this CSM2 UV phyto, and we're using a slightly older version of Wacom version 4. It's a little more stable than Wacom 6 with the soot injections. And we're coupling the tropospheric ultraviolet invisible or TUV model version 4.2 to Wacom. This lets us simulate the physical, chemical, and radiative consequences of these different aerosol injections into the stratosphere. And it enables us to compute surface UVA, UVB, and UVC radiation. And we also use Karma for the transport, removal processes of all the aerosols that we can inject using this Wacom and TUV setup. The TUV model is what enables us to calculate the UV radiation. So it calculates spectral integrals in line across 100 wavelength intervals between starting around UVC radiation, so 120 nanometers, up to the end of the visible spectrum at 750 nanometers. And it outputs spectral irradiance, spectral radiation irradiance, actinic flux, absorption by aerosols and ozone, super important, scattering by air, clouds, aerosols, Rayleigh and me scattering. And it also importantly computes these biologically effective irradiance or dosage rates, which can be sent to the ocean. So this E star INH is this, it could be seen as like a cell damage function, the accumulated damage to a cell by UV radiation. And we could calculate this using some biological weighting functions that we'll find in the literature. For the ocean model, we're using POP2, and it's coupled to the Marine Biogeochemistry Library, or MARBLE. We have 4 phytoplankton functional types, including small phytoplankton, diatoms, diazotrophs, and importantly, coccolithophores. And we also have 2 zooplankton functional types, micro and mesozooplankton, which they graze on the phytoplankton, and then the mesozooplankton graze on the microzooplankton, and that tends to control blooms pretty well. This 4P2Z setup is what we call it. And this enables us to simulate pretty well the biogeochemical response to the climatic extremes that we intend to simulate. So these biological weighting functions that I mentioned before is this, this lambda, this epsilon as a function of lambda. And so we scoured the literature for examples to use for our different phytoplankton functional types. Some of the research came from the 80s with the stratospheric ozone hole that opened up over Antarctica. So there was some research on Southern Ocean phytoplankton. We were able to find some functions for diatoms, coccolithophores, and then we found one for small phytoplankton, not much for diazotrophs. So we kind of generalized and used those 2 as the same. And so we are able to put this into TUV and calculate this E star INH parameter, which represents the amount of damage that would happen for a given amount of UV radiation. And then we convert this E star INH into a gamma UV, which is a UV limitation term. and it's related to this damage by 1/1 plus E star INH. And then we pass this from the atmosphere to the coupler, and then it has to go into the ocean. It is then attenuated with depth as a function of partially of chlorophyll, so there's some scattering. And for the most part, UV radiation only makes it 15 meters, 20 meters at most into the ocean. So this is an effect that's really at the surface. And then this limitation term goes into this calculation for photosynthesis of phytoplankton, which is computed as using this maximum growth rate as a function of temperature, multiplied by nutrient limitations, light limitations, and then our UV limitations. And then this is how UV affects the growth of phytoplankton in our model simulation. And so laying this out one more time in a nice little diagram, what we've added is this TUV section. Previously, the atmosphere model sends shortwave fluxes to the ocean, and then photosynthetically active radiation, which is what the phytoplankton actually use to grow, is just an approximation of shortwave fluxes times 0.45. In TUV, we have UVA and UVB. We can also send PAR directly, and this damage function goes right into Marble. We insert that into the photosynthesis computation subroutine, and then the photosynthesis UV affected is just the photosynthesis times that gamma UV. So that's the model development part of it. I also have some proof of concept simulations to show this tool in action, to show that it works, sort of. And so we have some simulations without UV radiation as a baseline. We have pre-industrial levels of UV radiation to test, make sure we're not breaking the model with the amount of UV radiation that's occurring in the pre-industrial. And then we have a massive UV pulse to really hit the system with a hammer and see what happens. And then this fourth one is, I'm not actually going to talk about this, but I have a talk tomorrow in the Paleo group at 1:45 p.m. where I'll be showing actual asteroid impact simulations. So come out if you're interested in that. So these first proof of concept simulations are showing this is a 5-year simulation, and it's a climatology over the course of a year of globally integrated phytoplankton NPP. So this black line is no UV radiation. The orange line is pre-industrial levels of UV radiation. So 1% change, and it's for the most part within the bounds of the no UV radiation simulation. So we haven't broken the model with pre-industrial levels of UV radiation, which is good news. This UV pulse case, we see a pretty substantial decline. It's nothing crazy, but 7.5% reduction in phytoplankton MPP from this pretty large amount of UV radiation. For some context and some nuclear winter simulations that I've been working on, there's around a 10% decline in MPP in maybe not nuclear winter, but nuclear autumn. So it's still pretty substantial with this UV pulse. Maybe more significantly is the redistribution, the vertical redistribution of productivity. So this is showing the percent change in NPP with depth over the course of a climatology for a 5-year simulation. And so as expected, you see this 20% decline in NPP at the surface, but there's actually a bit of a compensation effect at lower depths, simply because there's less phytoplankton closer to the surface. So there's less shading of PAR, letting more PAR get to the deeper levels. For the pre-industrial and for this UV pulse, there isn't this compensation effect doesn't cause the MPP on a global level to approach no UV radiation. So there still is a net negative. But in other simulations, I guess that's a spoiler for my talk tomorrow, it might make a difference. And then you can also see this in these maps where at the surface, there's entirely a decline in MPP. There's some spatial variability, maybe driven by the phytoplankton functional types, and if they exist in some regions more so than other regions, which is a lead into these plots, which are showing the spatial distribution of NPP under a pre-industrial amount of UV radiation. So you can see, for the most part, there's a decline in most regions, but what's interesting is the coccolithophores. The thinner their shells are, the more they're affected by UV radiation in this model. So in colder regions, they have a bit of a decline, whereas the small phytoplankton, they're competing with coccolithophores, and despite being affected by being bombarded by UV radiation, they actually see an increase in productivity in those same regions. So there's competition between phytoplankton functional types, and despite a uniform negative forcing, the phytoplankton are having different responses. And then if we look at the UV pulse, these are also not entirely shaped by the distribution of UV damage. Even under an enormous amount of UV radiation, small phytoplankton benefit in this great, for example, the Great Calcite Belt, where coccolithophores are typically very numerous in the Southern Ocean. And then diatoms benefit at the expense of small phytoplankton in the equatorial Pacific. So it has to do with their ability to compete with each other, and maybe also where they are in the vertical column. And that's basically it. This new setup requires modifications to the atmosphere, coupling TUV to the atmosphere, changing the coupler ocean, and sending it all to the ocean biogeochemistry models. Simulates a pretty minimal response to PI UV radiation and a moderate response to enhanced UV radiation. And the paper on this was submitted a couple of weeks ago and is still sitting there waiting for reviewer. Yeah, that's all I got. Thanks.
We have time for a question. Everyone? If not, there's our West speaker. Thanks.
Hi, everyone. My name is Alper Altuntaş. I'm a software engineer at the oceanography section at NCAR. And I'll talk about this work where we develop a new tool called Visual Case Gen. This is a graphical user interface that guides the users through the process of creating CESM experiments. And here I'm listing my collaborators, and I'll mention this is a project that was funded by an NSF CSSI award. And our initial goal here was to streamline the CSM simpler modeling effort. And the end result actually turned out to be quite useful beyond the CSM simpler modeling efforts. We wanted to enable hierarchical modeling where the users can explore and combine different complexity levels. And what these goals meant in practical terms was that we needed a tool for users where they could browse existing CSM configurations and also be able to quickly generate new configurations. And by configurations, I mainly mean here comp sets and grids, where they can mix and match models and settings in a compatible manner, and also create or modify grids as needed. So this will be a two-part talk. In the first part, I'll give a quick tour of the Visual Case Gen tool. Again, this is a graphical user interface guiding the users through the process of creating a case. And then the second part, I'll try to give you some insights into the inner workings of this tool. So let me switch to a Jupyter notebook. That's where this tool works. So yeah, here's a Jupyter notebook, and I'll hit start. And this actually makes it quite portable. Currently, I'm running this on my laptop, but it can actually run pretty much on any machine that CESM can also run on. And so initially, you'll see that there are three main stages here: the component stage, the grid stage, and the launch stage. And the tool will walk you through this workflow. And the first thing that the user needs to determine here is whether they'd like to work with a standard comp set that already comes with CESM or with a custom comp set. And since the custom option here is more interesting, let me go with that. And when I click on that option, you'll notice that more stages appear based on that decision. And next, I will need to pick a time period here. But at any time, I can actually navigate between these stages by using those navigation buttons. But yeah, going back to the time period, I'll go with this present day option, and that'll lead me to a components matrix where I can mix and match these different models to come up with a component. And I'll go ahead and pick my favorite model first. And then my next favorite model. Just kidding. And so I'll go with CAM, CLM, size perhaps, stop runoff, stop glacier. And the next is, so I'll need to pick my physics. So for most of these models, there's only one physics options already picked for me. For CAM and CLM, I'll need to pick from one of these physics. And then next is the component options where I can provide these optional modifiers. So there's this full list of modifiers for CAM 60 here that I can pick from. I'll go with this simple no modifiers option here. For land, I'll go with the SP, ICE, no modifiers. And okay, so that pretty much concluded the comp set selection. Now I'm on to the grid selection. And again, I have this standard or custom option here. Let me go with a custom grid as well. And here I'll specify a directory for my new grid input files to be stored. And I'll call this my custom grid. And now again, I can mix and match different grids. And here I'll go with F09. Well, by the way, I just remember I didn't demonstrate one critical thing here. That is that when I make selections, some of these options become unavailable, and that's because of the dependencies inherent in the model. And at any time, I can click on these unavailable options, and the tool will return me a reason behind why that particular option is not available. And I can go back and, revise my selections, or I can proceed with whatever is available. Let me restore all these selections. And again, custom. My custom grid, one, hit select. I'll go with FV1 degree width for the atmosphere grid. For the ocean, I have the option of going with a standard MOM6 grid, or I can create my own new idealized grid. And notice that the regional grid extent is not available, and that's because I can't read it because the Zoom is on my way, but the reason is a regional ocean model can only be realized if I don't work with size. And so here, remember, I picked size as my ice component, and that's why I need to go with a global ocean extent. Let me type in these high-level grid settings. My idealized to a degree is my custom ocean grid name. And when I click on this launch MOM6 Bathy button, another notebook will be auto-generated for me where I can review and execute the cells below to actually create these new MOM6 grid and bathymetry files. And I'll quickly execute all these cells in the interest of time. And the final step here actually saves the grid and bathymetry and mesh files. Now I need to go back to the GUI again, hit confirm. Finally, the land grid. Again, I have two options here. Let me quickly go with a standard land grid. And the final step here is actually to create this case. I'll enter my custom case 01 as my case name. And now I'm actually ready to hit this create case button, and that'll automatically do all the necessary steps, including modification of these CSM XML files to include the new resolution, new grids, running the create new case command, and running this case.setup command, adding all the necessary parameter changes. And it informs me that the case was created successfully in the path that I've specified. And so this is a quick tour of what can be done with this tool. And now I would also like to talk a little bit about the inner workings here. And so the first thing I'll try to explain here is how Visual Case Gen determines the compatibility between these different options. And this involves two things, a constraint specification and a constraint solver. And by constraint specification, what I mean is a new type of a metadata where we define relationships between different configuration variables. And what the solver does is it reads in these specifications, this new metadata, interprets that, and determines whether a given user input is valid or not. And for that solver, under the hood, I used an external library called Z3, and that's used for logical reasoning. And let me quickly describe what this library is. It's actually a multi-purpose library, but in the context of Visual Case Gen, we use this as a logic solver where it checks if a set of given constraints can be satisfied. And if that's the case, it can also return solutions. And it has some key relevant strengths, like being able to combine logical reasoning with knowledge about specific domains. And by domains, I mean things like bools, integers, reals, etc. And it can manage complex relationships between these different domains quite efficiently. And it's quite a powerful tool, widely used in academia and industry, developed by Microsoft Research, but it's open source and free, distributed with the MIT license. And in fact, they follow open development practices, so they welcome and even encourage community contributions. Has a robust Python API and quite easy to obtain. It's available via pip. And so I'll get back to the solver, but let me also describe at this point how we actually specify these relational constraints. And I'll begin with a simple example here, which basically says that this particular configuration variable must be a non-negative number. And notice here that this is a key value pair where the key is actual assertion or constraint, and the value is the associated error message. And if the user attempts to set this to a negative number, then the solver will return a error message, the error message associated with the assertion here. Another example, and this one basically says that the ocean component has to be either set to mom or the ocean grid mode has to be standard. And the interpretation here is that the custom ocean grids can only be generated for MOM6. And here the user picks data ocean, and that's why they cannot go with a new ocean grid mode. They have to pick a standard grid. And just to give an example of how expressive these things can get, here I'm specifying that if the land and ice components are stopped, then custom MOM6 grid must exclude the poles to avoid the singularity points in the MOM6 domain. And so this syntax, you probably noticed, is a bit unfamiliar at first. And that's because I'm relying on this Z3 Python API. And here's a comparison of ordinary Python operators versus Z3. And notice that the comparison and arithmetic operators are exactly the same, but the logical operators are slightly different, but not too bad. The string operators are can become different depending on what you're trying to do. But there's actually a more fundamental difference here. That is that the Python is an imperative programming language, whereas Z3 is a declarative tool. And I'm not going to get into the details of the distinction here, but what I really want to say is nicely summarized in this paper I came across, which says that building configurators using imperative programming is a nightmare. They're complex to implement and extremely difficult to maintain. And so declarative paradigm is a lot more natural and efficient fit. And so the syntax is unfamiliar at first, but I think it's a small price we pay to enable this Z3 as the core of our constraint solver. And so why do we need a solver in the first place? Why don't we, check each of these constraints individually to determine whether a user selection is valid or not? And that's because this constraint satisfaction problem is actually quite hard. These are famously classified as NP-complete problems, where there are a lot of edge cases, corner cases, like hidden conflicts, where all of your individual constraints might be satisfied, but their combinations can actually lead to unexpected conflicts. There's a case of dead ends where the user might find themselves in a situation where no options remain for a particular variable. You want to avoid those kind of scenarios. And there's also, from the developer's perspective, constraint analysis aspect. When we add in new constraints or make changes in the constraints, we want to be able to determine whether all of those constraints are satisfiable or whether we're actually over-constraining the system to a point that user cannot end up with a configuration. Or are any of these options unreachable? Are any of the constraints redundant? And solvers can actually allow us to ask these questions and get quick answers. And there's also the scalability and efficiency aspect. These are, again, complex problems. Each added variable increases the complexity exponentially, and so we need efficient solvers. And just to illustrate an example of a hidden conflict, here I have two constraints. The first one basically says that the WaveWatch3 wave model can only be picked if either pop or mom is the ocean component. And the second one says that if the user wants to pick stop atmosphere, then they also need to pick stop ocean, because you need active or data atmosphere to force the ocean model. And you might guess where this is going. If the user picks WaveWatch3, then the stop atmosphere option becomes unavailable, even though there isn't an explicit constraint specifying that WaveWatch3 and stop atmosphere cannot be coupled. It's the combined result of these two constraints. And we need to be able to capture these type of situations, and the solver does that. And it's not always as simple as this. Here's another example of a hidden conflict now involving 5 of these different constraints. And the violation that I'm going to show here is the end result of all 5 of these constraints. If you were to check these individually, you would not be able to determine that there was a conflict here. And so the bottom line is that the interaction of these constraints, even those that are simple, can lead to hidden conflicts, dead ends, and chain reactions that might be hard to predict. And so that's why we need robust constraint handling. And so I'll shift the gears a little bit and talk about some software design aspects of Visual Case Gen. And in particular, I'll describe this stage mechanism. And by stage, I'm referring to a collection of configuration variables that can be configured simultaneously. And here you see a representation of one of these stages, the components stage. And this is a hierarchical concept where a stage might have a parent or siblings or children. And based on this hierarchy, a stage tree gets generated. Here's the full stage tree for Visual Case Gen, including all of those stages. And what's perhaps more important is that that tree gets transformed into a stage pipeline that determines the sequencing of each of these stages, beginning with the component set stage and ending at the launch stage. And the user can take different paths along this pipeline depending on what the modeling needs are. And so this pipeline is crucial because it dictates the variable precedence such that the variables in earlier stages have higher precedence and variables within the same stage have equal precedence, which might sound simple enough, but there's a complicating factor here. That is that the same variable can appear in multiple stages as long as they're not reachable along the same path. And so one of the necessary requirements to end up with a consistent variable precedence is that the stage pipeline must form a directed acyclic graph, which also ensures that there are no cycles encountered by the user while they're configuring their case. And so now let me combine the stage mechanism and the constraint solver here. And so when you combine the two, you end up with another data structure that's crucial here in Visual Case Gen, and that is the constraint graph, where each node is the configuration variables. So for any given variable X and Y occurring in the same constraint, we draw an edge from X to Y if the precedence of X is greater than or equal to precedence of Y and vice versa. And here's that full constraint graph for Visual Case Gen, including all of the configuration variables that a user can control. And the edges between these variables determine the relations and dependencies. And when a user makes a change in one of these configuration variables, that initiates a traversal of this constraint graph, and that's done by visiting all of the potentially affected variables. And for each of those variables, we call Z3 to check if the validity of any of their options have changed. And this traversal only propagates to the nodes that are potentially affected, and that depends on the user input, the stage hierarchy, and the constraints. And just to give an example of a traversal, here the user picks mom as their ocean component, and that'll initiate a traversal of this graph, starting with the ocean component and extending to all of the potentially affected variables. And once the traversal is complete, the front end gets updated with the new validities of these options to communicate that with the user. And so that was a high-level overview of two really crucial mechanisms in Visual Case Gen, the constraint satisfaction problem solver, and then the stage mechanism. And in the next few slides, I'll try to share some insights into software design and development that I gained while I was working on Visual Case Gen. And the main idea here, I think, that I will try to convey is that the conceptual construct of these software systems that we develop matters a lot. And here you see on the left the initial prototype of Visual Case Gen. On the right is the current version. And there's a big difference here because the stage mechanism wasn't incorporated in the initial prototype. And with the introduction of that concept, the tool and the code got really a lot better. The user experience has enhanced. There's clearer guidance now. Robustness increased because now I have a clearer idea of the requirements and invariants like variable precedence, state change rules, and relational dependencies. Maintainability improved. We ended up with a better performance because now that I had more clearer idea of the requirements, I could implement more aggressive optimizations in the solver, which effectively tripled the computational performance. And so then the main takeaway here is that software architecture is something, in my opinion and experience, is something we rarely discuss or consider, especially in the scientific software community, where we tend to focus on low-level coding tasks. But high-level design constructs like the stage mechanism I mentioned, these can be functionalities, patterns, structures, really have a significant influence on overall software quality. And so the message here is that we should make sure that all of these conceptual constructs are clearly identified. We need to make sure that we're not missing any of these high-level constructs, incorporate them, document them, and the relationships between them are well established and understood, and the requirements entailed by those design decisions are carefully analyzed and adhered to. And this goes back to this famous article, No Silver Bullet, from the 80s, where Fred Brooks says that the hard part of building software is the conceptual construct and not the labor of representing it. And I think this is even more relevant now with the introduction of tools like GitHub Copilot or other AI-generated or AI-based code generators. And what those tools do is they make the easy part easier. Now we can use those tools for low-level coding tasks, but the hard part here is getting harder as a result of that. And along the same lines, another quote on, so this a professor at MIT, Daniel Jackson, who thinks that the agile method might become less relevant soon because the agilistas prioritized coding tasks over things like design requirements and specifications. But in 10 years, he says, those will actually be the only things we'll write. Low-level coding will be done by, AI-based tools. This is probably overly provocative, partly because what the agile method means depends on who you ask. And so this might not actually, apply to your perception of the agile method. But I think the main point is a good one. That is that we're going to spend less time on low-level coding tasks, but we also have to spend more time on design and requirements and specifications if we want to improve our productivity using those tools, and also at the same time keep our software quality intact. Some of the references along those lines, especially the first one here, again from Daniel Jackson, The Essence of Software, is highly recommended. And with that, two quick announcement. A stable beta version of this tool is available at this GitHub repository. And then official release is upcoming this winter. And with that, I'll stop.
We have 3 minutes until lunch if there are any questions.
Very nice talk, Alper, and very nice work. And I appreciate you really talking about design because I think we need to do more of that. And I appreciate all the work you spent in getting a good design here. That's really awesome to hear about. So just a couple easy questions, I think. One is, can the tool make surface data sets?
It can't do surface data sets from scratch, but it can modify existing.
Oh, can modify existing ones.
It's what FSR does, right?
Yeah, it just modifies them.
Yeah, it has an API to run FSR modifier tools.
So I think but it probably could be changed so it did. Now, it would have to submit a job to derecho or something. Is that a possibility?
Right. Yeah.
That could be. Okay. That's awesome to hear. And then just another really simple one. You showed the example of a -1 being not allowed. Does it also know about upper limits for certain things?
Right. I don't remember the name of the variable, but there's one that needs to be between 0 and 20, right? So those are
PFT,
all, those are all specified as constraints.
Oh, okay. Oh, it's specified as a constraint. Right. And so I could look at the constraints and see what.
Sure. So, but yeah, that's a good point. So far, I've been the only person adding those constraints. And if we could have like more pairs of eyes and more collaborators and more people to add onto those constraints, that would be great.
Oh, okay. Yeah. Because that particular one, it depends on, the number that you can go to depends on some of the other choices. So we can capture those type of dependencies with the, right, exactly. Yeah. And I could work with you on doing that. So that's awesome. Thank you.
Thanks.
Are there any other questions? Okay.
That's really awesome. Okay. This is kind of a stupid, silly question, but can you, the part where you have the comp sets that you're picking or the components, is there a way to have like the hover, like add hover text that has like more note? Because one of the big things that I find when I'm working with new users and even myself still, I'm like, what is this again? So it might be nice because a new user might be like, I don't know what I'm picking.
Right.
And you could like have like hover text. It's like, this is like this.
Yeah, actually the mechanism is there.
Yeah.
And I have that feature for some of the selections for the physics and models. What I did was when you hover on those options, it gets the descriptions from the XML files, but the descriptions are not very descriptive. So when you hover over Chem 60, the description you're gonna get is Chem 6 physics, which isn't helpful.
Okay. Okay. So maybe we could,
Yeah.
That's on us.
yeah, maybe.
Incentive to improve the description.
Thank you.
Well, thanks to all of the speakers in this first half. We have an hour for lunch and then we'll be back at 1:30 for more talks. June, Jason, and Helen, if you're online, if you could just stay on for a couple of minutes and make sure you can share your screen and all that works. Thanks.
All right. Not good. Okay, welcome everybody. We're getting ready to start. So we have 3 remote presentations coming up. The first one is going to be from June Wang of NOAA Environmental Modeling Center on asynchronous I/O. So June, all yours.
Can you hear me?
Yes.
Thank you. Okay. Okay, good afternoon, everyone. My name is Jun Wang. I will talk about the asynchronous I/O component in UFS weather model. Those are my co-authors. We have been working together with ESMF group and also some discussions with Jim. Thank you all for those development and discussions. Here I will talk about the current capabilities of the asynchronized write grid component in UFS, which is a very important feature for operational models. And then I will talk about some initial effort on developing generic write grid component and some future plans. Develop asynchronized I/O component in UFS is critical. For us, I/O performance is always a challenge. The reason I listed here, first of all, there is a restriction for the operating model to finish within a certain operational windows. For example, for GFS, we have a limit to finish the model runs 6.5 minutes per day. So every 6.5 minutes, you have a forecast day results coming out. So that we all know outputting model history files takes time. Originally for operation model, which are 100 kilometers to today's, we have 13 kilometers output history file is still a challenge. Especially for operational settings, those files need to be show up for the public at a specific time. You cannot delay for first output time showing up late or a certain forecast output showing up, say 15 minutes late is for us a incident. Model resolution keep increasing. That also add a challenge, and the amount of output data has been increased significantly. I will show some data later, so you will see. Synchronized write grid component will allow us to separate the forecast integration from the data writing part. This is allow us to have increase the basic speed up the forecast run, and also let the writing data can be catch up. So that is a technology we have been using in the past. The first implementation of asynchronous write grid component with inline post is in GFS version 16. And later on, it also was used in GAPS version 12 and GFS version 16. And the capability later has been extended to HAPS version 1. Here is a schema to show the parallelization of every three ATM write quit component. Right now, the asynchronized IO only was only implemented in the every three ATM. So on the left side, you will see the forecast grid component running a certain task from P1 to Pn. And then we have the right grid component, which can have several. And for each one, each right grid component, it takes the forecast output at a certain forecast time and creates the history files and also the post products. So you will see, for example, we can add a second group for the right grid component to handle the second output time. And depends on the how fast is the writing, you can have multiple write grid component. That gives you the flexibility to choose how many write grid component you need to catch up the forecast. Later on, this capability has been extended to the write component to handle a more complicated configurations. In the previous figure, you see we only have one forecast grid component. In HAF's case, they have a parent domain, which is a parent forecast grid component. And in this domain, you also have static nested grid component. So that is a separate domain. You can also have moving nest. And then you will have another nest grid component with moving domain. I want to mention the static domain, also the moving domain, they can have several. So it's not just only three. To handle those outputs, so we have been extending the capability. As you see, the parent domain can talk to a write grid component, and then on the write grid component, you will process the data from the parent and from the the nested domain. And it will have different process. For example, if you have static and you want to directly output a different grid, you use regrading. But for moving domain, because the forecast domain is moving, so we first redistribute data on the write grid component, and the write grid component will figure out where is the domain now, and then it will regrade to output to the output grid for that domain. Here are some results. This is the IO improvement in GFS implementations. The first one is for GFS version 16. As you see, when we output the data at 13 kilometer and 127 vertical levels, previously in GFS version 16, we're using namesile, which is a binary data. When we move to NetCDF, the same data sets, but writing time increases dramatically. And then we tried first use the lossless compression to reduce the data. You see it reduced the data set, but the writing time increased, tripled. And then after we implement the lossy compression with parallelization, and then we finally get 6.3 GB data, and it finished in 34 seconds instead of 960. So that is a big improvement for GFS version 16. Here I also show some inline post. As you see, inline the post processing can be done on the write grid component. This way, it will save some time for reading if you run the post processing offline. So the time saving for high resolution runs, you can see it's 39 seconds versus 211 seconds. Here is a figure shows asynchronous IO component in HAFS version 1. So we implement this for HAFS version 1 with moving nest. So you see this is parent domain on the left, and the middle is a static domain, and on the right is a moving nest domain. So when the model is running, you will get exactly the output showing here at the same time. Now we have a challenge when we move to the UFS coupled configurations. Here I want to show you what we have been tuning for a coupled configuration case to have balanced overloading. As you see, there's many kicks here. The reason, especially for, in this figure on the left, blue lines are ATM for component running time, and red is ice running time, and the yellow line is for ocean. As you see, the kicks are always related to the I/O activities. Sometimes you have history output, sometimes you have restart output. Because of this, as you see, the waiting time we showed here on the right, the ocean has to wait a lot because ocean output time, when it happened, we do not want to have atmosphere and ice wait, because atmosphere actually takes lots of resources. Because of this, we would like to see if we can develop a generic I/O component, asynchronous I/O component, we can remove those kicks. So that means that we only need to consider the forecast time, and when the model needs to do the I/O, it will dump out to a separate write component, and those write component will not participate in the coupling activities. So we start to have some discussion with the modeling community and to collect requirements for a generic asynchronous output. And the discussion is focused on developing a asynchronous generic write component in other Earth modeling components. And here I listed several requirements we collect. And basically, we would like to have a model component communicate one or more write components. As you see, when you have multiple components, you have the flexibility if the I/O is slow. And also the write component receives self-describing output files. The write quick component, it only handles data. It does not need to know exactly what data it received, because the data itself describe what the field is. Of course, write component should handle output grid, because output grid could only be known to the write grid component. Also, there is interpolation or redistribution data, and write grid component need to handle, for example, additional data process like inline post, and it can output files at different forecast time and also at a specific frequency and so on. So with the discussion, we come out of 3 approach. The first one is a new WAPC component. So implement the write grid component as a new WAPC component or a ESMF component. We also discuss the possibility to implement asynchronized writing through PIO. So some initial testing with this idea of generic I/O. Here we tried to set up a initial test with new WAPC write component. On the right, you see the run sequence. Basically, use a I/O components. As you see, we have the ICE-IO in red, and then this ICE-IO can run synchronously with the ICE component. So basically, we can see the restart files created from this one are identical from the current restart files created by Site6. But there are some temporary workaround in order to make this happen. And so for the future work, we have been discussed with ESMF team to if they can develop a prototype in WAPC write component, especially resolve those temporary workaround we have used in order to test the idea. And there are some challenges, and including handshaking between the model component and write components, and simplify the run sequence, and so on. Additional code changes need to be made in several model components. As you see, if the model component needs to provide the data to the write grid component, then the model component itself needs to prepare the self-described data. So that needs more communication with the authoritative component model managers. We are continue testing the performance, especially in the coupled configurations. That is all from me. Thank
All
you.
right. Thank you, June. The questions here are online. Okay.
Thank you for your talk. Thank you for your talk. And I'm wondering about an aspect of that because I love that you're working on this in a right component because this is useful for all ESMs. Would the right component be within, like, would it be within CAM? I mean, one of the things that in CSM, we try to just pass coupling fields, just the surface fields that are coupled between model components to the coupler. And so we don't send the extensive 3D fields to CAM, but I'm guessing this right component might be a subcomponent of CAM, for example.
It can be. So
Oh, it can be. Okay.
Yeah. The idea is for any model component, you can have a generic IO component. So that component will take the data you want to output, and then the forecast can continue.
Okay, cool.
Another approach would be to have the 3D fields go through the coupler.
All right. Thank you, June. So we're going to move on to the next talk, and that's going to be by Jason Boot. So Jason, you can share your screen.
Okay. Can you see the screen now?
Yes, we can see it.
Okay, great. All right. My name is Jason Boutte, and I work at Lawrence Livermore National Laboratory for E3SM, and specifically I work on SEAM. And so today I'll be talking about modernizing SEAM. A lot of this work is supported by Jim Fukar, Jim Edwards, and Rob Jacob, and a lot of other external collaborators. And so first I'll talk about SEAM, which is the common infrastructure for modeling the Earth. And this tool is basically, it consists of two main features: the case control system, or CCS, which is essentially a way of encapsulating all of the information that's required to configure, build, run, post-process model data, and then archive. And then the second feature is system tests, which allow a user to test a specific case, generate and compare baselines, and check that the model itself is bit for bit, or be able to see what has changed in the answers. And so with modernizing SEAM, there are two main goals that we're looking at, which is improving the user experience and then modernizing the actual code base itself. And so at this point, the code base is around 9 years old, and we want to ensure that we're keeping up with modern Python standards, especially what's being supported within HPC centers. And so as I kind of talk about these different goals in the tasks that we have, there'll be some included timelines on when they'll be accomplished. And so I'll start going through those. With improving the user experience, the first place we identified was documentation. And so there's a lot of documentation within SEAM, and it's fairly well organized already, but it could be improved upon, especially to really drive home the idea that there's these two main components, and we could update this organization. And another area we could do improve on is updating the documentation itself. There's still some documentation for components and features that were removed from SEAM. And there are also features that were added that were never really documented. And so along with that, we also want to add like an FAQ and some additional kind of example area about using SEAM. The next area we are looking at improving upon is the consistency with CLI arguments. And so SEAM provides around 57 tools, and there's a lot of arguments within each one of these tools. And a lot of them are interoperable, and they affect how other things work. And so one of the areas we want to improve on this is by grouping these common arguments and really making the user interface through the CLI cleaner. And along with this, we want to review the actual descriptions of the arguments themselves and ensure that they're showing how they're related to other arguments and how they might actually affect the tool that you're invoking. And so the next area we're looking at improving upon is logging and error handling. And so within SEAM, there's a lot of verbose logging. Some of it can be noise, a lot of it with validating XML. And to improve upon this, we could really utilize the log levels in a more efficient manner, and then add in some filtering so you can kind of drive down to what you're looking at to get out whatever error or messages you're looking for. The next area is error handling. There's still instances where Seam will be running on the batch system, or the model will be running itself, and some error propagates up, and it may not be very clear and sort of ambiguous. And so we want to ensure that we're always passing back an error to the user that will properly describe what's going on and potentially ways of resolving it. Another area that we want to look at improving is a public API. And so currently you can import Seam into a Python file and then manipulate a case, but it was never really designed with that intent. And so it's not very well organized or documented. And so we'd like to go in and clean this up, provide a lot of good documentation, and then make this something that's really accessible to the user. And this is a great feature because it's, allows you to orchestrate and automate case creation, customization, and it sort of not replaces, but can be used instead of, say, a bash script, which is kind of traditionally used now. And by using Python, you then get opened up to the entire Python ecosystem. Another area that this can be used is to extend Seam. And this might be to build a tool that, say, manages ensembles, which is something that's going to be looked at. Another area that we're looking at potentially proposing is building a CLI tool. And so this would, right now, a lot of the tools sit within the Seam repository or are linked within the case directories. And this would create kind of a central tool that you can use from any directory, and it would kind of detect where it is. But it would allow you to run a lot of the common subcommands like create new case, builds, XML query, XML change, and really provide kind of a single entry point into manipulating and using Seam and manipulating cases. And so with that, there are a lot of tools, a lot of Seam code and tools that live within a case. And by using this sort of tool, we can kind of clean up a lot of those symlinks, since they'll be kind of accessible from anywhere, and really make these cases kind of more portable. And so this has kind of a side effect of increasing the portability. Right now, you can take a case and pass it along, and as long as it stays on the same system, it's fairly usable. But the symlinks, if you take it and you take it out of whatever model you're using, it might, the symlinks won't work. And by removing these, it becomes a lot more portable, whether it's on the same system or potentially between systems. Where, excluding build directory and run directories, we could potentially have a migrate tool to migrate a case to a new host. And so along with providing us the CLI tool, we would also look at having a PyPy and a Conda package. And so currently the way that Seam is mostly tracked with the model that's using it is through a submodule or by cloning the repository itself. By having a normalized kind of release cycle, and having these packages, you could then use a requirements.txt or environment YAML file for Conda. We'd also look at doing something like a weekly release cycle and kind of constrain the versioning down more to encapsulate the changes that are coming out. So now I'm kind of moving on to talk about modernizing the code base itself. The first area we kind of identified was refactoring the code. And this was kind of identified by looking at the cyclomatic complexity of the code. And this was via the McCabe tool by using another tool called Prospector. And essentially this identified 52 functions that are considered complex. And really quickly, the McCabe tool will give out a value. Anything above 50 is considered very high risk or untestable. And then everything below 50 is kind of classified into high risk, moderate, or little risk. And so 54% of those were moderate risk, 44% were high risk, and 2% were very high risk. And so we'd like to go through and refactor all of these functions to break them down into smaller components, increase the unit testing on them, thus improving the code coverage, and making Seam overall a more reliable tool. And so another place that we're looking at updating the code base is within just the styling of the code to make it something that's more manageable and readable, and ensuring that we're staying with the most current supported Python stylings. And so we ran a bunch of static analysis tools on this to identify areas that could be improved. And one of them was Pylint, which generated about 1,848 messages. Once we kind of bin these into what unique messages they were, there are about 68. And so these are kind of spread out and duplicated a lot throughout the code. And some of the warnings are kind of trivial, but a lot of them could really improve the code quality itself and improve readability and ensure that we're using the features of the most up-to-date supported Python versions. Another tool that we used was PyCodeStyle. And so this uses the PEP8 standard to look at the styling, and this came up with 86 areas that we could improve on. And so this is just somewhere else that we'd like to address to update the code itself. The last tool we looked at was Vultr, which identifies unused code. And this came up with 7 variables and 40 functions and then 8 attributes. And so now, once these have been identified, these are areas we'd like to go through and ensure that we're not using them. And if we're not, then remove them and make sure that we're working with a slimmed down code base and only testing what we're utilizing. Additionally, with modernizing the code base, we'd like to this sort of user-facing feature too, which is removing model-specific and driver-specific code. And so we have made one pass with the model-specific, but there were some areas that were missed. And so we'd like to go back through, remove this model-specific and driver-specific to have it live within its respective repositories, which would greatly increase the efficiency for users in needing to change, different settings. You no longer have to go in through Seam, make a PR, and then wait for that to kind of propagate its way up. The next area we'd like to improve is fixing the unit testing. And so right now, there are some unit tests that are broken because they rely on previous test cases. And so we'd like to clean those up. And this will really improve like the efficiency through testing, through GitHub Actions, or even testing locally. Another area is reorganizing the modules. So with building this more public API, we'd like to reorganize a lot of the internal modules and kind of make sure they're grouped by functions and that they kind of represent the idea that there's these two main uses for Seam, or features within Seam. And then we'd also like to look at breaking out reusable code. There's been some interest shown at reusing some of the code that's within Seam. And so again, with building this kind of public API, these areas that we've identified as being potentially reusable code, we would break out in a fashion that a user could come in and install Seam and then use these tools in another project. And then lastly, we are looking at proposing some optional replacements for the test scheduler and workflow. And so this would allow us to potentially use as an optional dependency some different technologies like CWL, the common workflow language, and some tools to manipulate and submit, say, CWL workflows like Toil, or even using a tool like TaskGraph that handles managing long-running tasks. And so with accomplishing all this, we're hoping to, improve the user experience and make the code base something that's manageable and maintainable, for years to come. And here you can find the link to the Seam's GitHub, the docs, and then a link to open up some new issues. And we invite, anyone to come in if they have feature requests or suggestions or anything, just open up something there. And now I'll open it up for questions. Thank you.
Thank you so much. Questions, comments? Yeah, Jim.
Jason, thanks. This is great. And it really brings home the point that software is not something that you develop once and it's over. It's an ongoing cycle that needs to be continued if we want to continue to use the software. On the workflows issue, I wonder if you've looked at more modeling or geophysical model oriented workflows like Silk and ECFlow, as opposed to the ones that you listed there?
Yeah, I mean, I'm definitely open to look at some of those. I've looked at some of them. They didn't get included within this, but yeah, Silk is one of them that I've looked at, and it's definitely something to consider using.
All right. Thank you so much, Jason. Sorry for mispronouncing your name at the beginning.
That's okay.
Yeah. All right, then we're gonna move on to the next talk. That's by Helen Kershaw. Hopefully I'm saying that one right.
Oh, perfect. Yeah.
All right, thanks. Go ahead.
All right. Hi everyone. Hopefully you can hear me and see my screen. So I'm Helen. I work in the data assimilation research section here at NCAR. And I'm going to talk about CESM DART and some updates on assimilation for Earth system models. So there's two topics I'd like to cover. One's our experimental project with 2 SciParks interns this summer, and the other is a large collaborative project between NCAR and Woods Hole Oceanographic Institute called Crocodile. So it's a large project. Dan Amrine is the PI. It's a CSSI project. Lots of cool stuff going on with regional ocean modeling, but I'm going to cover the DART part of the project. Since I've started with a bunch of acronyms, here's what they mean. SciParks is CISLs, so the Computational Labs Summer Internship Program. DART's the Data Assimilation Research Testbed. NUOPSI, National Unified Operation Prediction Capability. And Crocodile, which is kind of a forced one, is the CESM Regional Ocean and Carbon Configurator with data assimilation and embedding. And CSM, hopefully everyone knows already. So just like a quick rundown of ensemble data assimilation. You run a bunch of model forecasts. So an ensemble, because you're interested in statistics. You take some measurements. So you measure an observation with an associated error. And you combine those to get an improved estimate of what's going on. And you do that over and over again. DART is the particular piece of software that we use for ensemble data assimilation. Here's a super quick rundown. We've got leading edge data assimilation research, collaborators throughout NCAR and the world. It's really interesting because you have to go fast. This example is like people flying at severe weather, and they want their assimilation finished so they know where to go next. So it's really good for improving models. You want to combine models and observations. You want to think about how predictable things are. Data assimilation is a big part of NCAR's mission. So here's our dramatic promo slides. Check us out if you're interested. And just a couple of shout outs to some other DART talks going on. Julie has done a bunch of stuff with land data assimilation, so assimilating new satellite products into CLM. And improving the organic carbon cycle, where the carbon goes, which plants. And then Moha has got a poster all about the algorithmic developments we've got going on with DART. So we're actually able to do non-Gaussian data assimilations. That's super exciting, particularly for people interested in convection and things like that, and pollution and traces. We've got hybrid, to sort of half 3D var, half ensemble, and stuff with sampling errors. And Kevin has a poster which has a bunch of applications. I've just highlighted one here. This is from Andy Fox, and they were actually looking at how COVID and the reduced aircraft flights had a big impact on observations and forecasts. So back to why I'm here, SciParks and Crocodile. So let's take a look at the SciParks project. So this is a super ambitious project for a couple of interns. And so the goal, I guess the title, is on optimize ensemble data assimilation performance for coupled Earth system models. So they're having a look at NUOPSI, ESMF for DA, and comparing this to the traditional way we do it. So the 2 interns are Ang and Suman. Really good. Dan and myself are the mentors, but I really do want to give a massive shout out to the SMF team and Jim and Alpa for being super helpful with this, like I said, somewhat crazy ambitious project. And I guess here's the summary. It's quite interesting to hear people talk about ensembles and Zeem and NUOPSI IO. But yeah, this is what we do at the moment. So essentially every CSM data assimilation runs like this. You advance an ensemble of models, and then the model is just going to dump all this data to a file. DART's going to ingest that across the whole ensemble because we're interested in statistics. It's going to ingest all the observations for the particular time window you're interested in. So typically every 6 hours of model time, every 12 hours of model time, something like that. DART's going to update state. So like rewrite those netcdf files with some slight changes, and then the model starts up again. And you do that over and over again. So it's lots and lots of data movement. We tend to call it transpose, and it's all through the file system at the moment. And I guess the goal of this project is just to experiment and kick the tires on what happens if you don't go through the file system, right? What happens if you can use UOPSI to pass the data in memory? So you'd advance the model, we're still going to ingest observations, and then, you know, we update through the UOPSI and the mediator. So there's still lots of data movement, right? Like we haven't, you know, we're still moving a lot about, we're moving, you know, whole states of data, but the idea is not to go to disk. And so we got the students just working on some prototypes of this, and getting some ideas of the measurements, how it's going to perform, what's going to be the crux. Yeah, super exciting. And then next up, Crocodile. So this is a 5-year collaboration. So it's a CSSI project between NCAR and TUI, which is Woods Hole. So it's a software infrastructure project. So the goal is to provide something for rapidly configuring regional ocean modeling. And I've stolen Dan's slides for this explanation. So we want to support ocean biogeochemistry and using Marble, which I'm sure a bunch of you are familiar with, and also DEER with Dart. And sort of to boil this down, like we want to make increase the usability, you know, infrastructure that takes these global models, these massive dynamics, data assimilation, which can be hard to set up, boundary conditions, all that stuff that's hard to get going, and boil that down into something you can understand locally. So that's the goal. And it's been sort of the test case, or like the sort of target we're starting with, is this novel observing system network, Ocean Vital Signs network. So this is where WHOI comes in, big picture. They have new instruments, you know, super expensive instruments coming online, and where do they put them to get the most bang for their buck, right? They want to understand how the ocean's evolving. They're particularly concerned about like carbon cycling and people doing like carbon, I guess, sequestration into the ocean, and what would be the effects of that, and could you measure it? So all sorts of super exciting stuff. And the Ocean Group are super involved in this. Like I say, I'll reach out to Dan if you want to know more. And I guess I'm just going to talk about this tiny bit of it, which is PyDart. So Dart, as I keep talking about, is, you know, we have these two things to think about. There's state space, so that's the model. And we work with an ensemble, so it's, you know, a bunch of model runs. And there's this other way we think about things, which is observation space. So a lot of times what we're interested in is what you actually measured, the observation, and then what the model or each ensemble member thinks the observation should be. And the difference between those two, we call observation space. And you know, it's really used to look at how well your simulation's doing or how biased your model is. So they're really, really interesting diagnostics. So state space, pretty good with. Got this MOM6 interface. It's available now if you want to play with it in preparation for CSM 3. And then this observation sequence, this observation space stuff, we have a bunch of observations. Like I said, there's like billions of observations already processed for, you know, 20-year reanalyses. So we've got all sorts of observations, and they're in this obsequence format. So it tells you what the observation is, where it was, the time it was, the quality control, the error variance, any metadata needed to calculate forward operators. And that's what goes into Dart. And then what comes out is all your input information, and also a bunch of assimilation information. So this particular example is just, I've just put a few sort of demo bits to show you. So you might be interested in the prior ensemble of the forward operators, posterior, all the ensemble members, maybe just the mean, maybe just the spread, but sort of various bits of information about about the observation and the forward operators. So that's what the model thinks the observation should have been. And you might, if you're doing like perfect model experiments, so you might be simulating what a new observation, I know like the ocean vital signs network, you might simulate what that looks like, with synthetic data. And so you might have a truth. And then there's just a side note, there's like an additional complication with observations that they can have a bunch of metadata. So this particular one is a satellite radiance. So you need a bunch of information about the frequency, which particular satellite it was, the azimuth, all that jazz. And traditionally, how we've dealt with all these observation-based diagnostics is with Fortran to do all the binning, and MATLAB to do all the plotting, which is okay, right? I mean, people have done a lot of really good work with this, but I think binning observations and sorting and grouping and qualifying is you probably only want to do it in Fortran if you're a masochist. And MATLAB, particularly for Crocodile, we can't use because we need to produce this sort of open source tool that anyone can change and anyone can use and have it be free. So we're pivoting to Python. That's where PyDart comes in. And so we want to ingest these ob sequences with the self-describing, slightly clunky format, and output something people can use in their favorite Python tools. So at the moment, we've got this, I guess, start of it, and we're producing a data frame so people can interact with it with their favorite tools. The idea is we want to give people, something in their language. So the language of data science makes it quite user extensible for diagnostics. So the contract is here, right? As long as we produce something that takes observation sequences and produces pandas, or probably it's going to be something like X-ray tools, we can change this format. So it's a really nice split for us. We can improve this format without breaking people's diagnostics. And I guess, this is kind of my cry for help, really. So I guess I'm at the requirement stage, particularly with Hui, because we're really focused on the ocean for this project. What diagnostics people are interested in, what existing tools we can plug into, like Cupid, Melody's Monet. My big thing is I want to try the big data problem. Like I say, we've got 20 years worth of reanalysis to play with. And a couple of next steps, we might end up using this as pre-processing. So like subsetting observations, especially by type of ops. And I guess just to prove it, this is actually genuinely a notebook. It's got some nice interactive plotting. So, essentially like all your useful Python tools we can set up. Anyway, that's all I was going to talk about. Feel free to ask me any questions. If you've got any way better ideas of how to do this, I'm super interested as well. So do reach out with your analysis, diagnostic thoughts.
All right, thank you. Anybody has any questions or diagnostic ideas or tools we can plug in? Okay. Well, just a question, is CSM sticking with Dart for data simulation, or are any tools like JEDI in the horizon for CSM?
I know JEDI has like JEDI MPass. So I don't know if some of the high res is going with JEDI MPass, but I don't think JEDI supports a lot of CSM models yet. Whereas Dart supports a bunch.
Sounds good. All right. In that case, thank you so much, Helen. We're going to move on. So our next presentations here from the room, and will be by Alex Pinnard. Probably want this object. That's your monitor here. Hold on to it. Let me get my phone.
This goes next. Great. All right. Hi, everyone. My name is Alex Pinnard. And today I'm going to be talking about some work we've done towards training statistical models to identify optimal loss of compression parameters on some CESM data. And this is work I've done with my collaborator who's here, Allison Baker at NCAR, and Professor Dorit Hamerling at
the Colorado School of Mines and formerly also at NCAR. Okay, so just a little bit of background real quick. So I think as we all know, climate simulation models such as CESM are used in large scale projects such as CMIP6. And the total output size of a lot of these model ensembles can be really, really big, in the order of petabytes. It turns out that it's more efficient to sort of pay me to try to reduce the size of the data rather than to just buy enough storage space to store all this data. So my goal is to try and fit that data into as small of a space as we possibly can without systematically altering them in any way that scientists might notice. And one kind of tricky aspect of this is we don't really know in advance what all the kinds of analyses are that are going to be done on the data. So the easiest way to reduce the size of the data is to apply lossless compression. Unfortunately, this doesn't work very well on floating point data because there's a lot of kind of noise, randomness in the least significant bits of the data. So lossless compression doesn't work very well. And that, as a result, means that we have to compromise on some combination of the time span, the spatial and temporal resolution of our output data, etc. And using lossy compression, which is what I'm going to talk about here, is a way to more greatly reduce that data size, but does come at the cost of some of the data quality. We lose a little bit of information as we're compressing the data in a way that can't be perfectly reconstructed. And so, of course, scientists are understandably concerned about the effects that this can have on the results of their analysis. So we kind of have a few approaches we take to sort of make sure that we're compressing the data safely. One thing that we do is to try and reduce artifacts in the data by collaborating directly with people who produce these compression algorithms, like Peter Lindstrom, who produces the FP. And also by compressing each climate variable individually and even each time slice individually to try to preserve the spatiotemporal properties of the data as best we can while keeping the data small. And finally, working with application scientists so we can provide tools that allow them to see the effects of compression on their analysis. And this picture kind of shows what happens if you sort of really blindly compress the data at a really aggressive level, and the results can be pretty bad. So common metrics we use to compress the data, such as the root mean squared error, peak signal to noise ratio, maximum error, are not necessarily sufficient for these types to capture these types of spatial or temporal errors that might exist in the data. So you can see, looking at the plots, that we have these spatial errors that are really heavily correlated with each other and could potentially introduce some error into an analysis performed on that data. So we need more specialized metrics that can be quickly computed on the data. An example of one of these that you can use is called the structural similarity index measure, which is a measure essentially of the visual similarity between two images. And this measure is performed by sort of taking a rolling window of pixels across this image and comparing the relevant, what the authors term of the SSIM term as luminance, contrast, and brightness, which in the end are these S1 and S2 terms in this equation that ultimately boil down to comparing the mean, the variance, and the covariances of each of these rolling windows and sort of averaging them. What we use is slightly different. We use the SSIM for data, or the DSSIM, which is similar, but operates directly on the data set, which bypasses the need to actually create an image, which is very computationally time consuming, and also is more independent of the plotting parameters that way. So this metric works kind of similarly to the SSIM in that it's providing us a measure of the data set similarity, and it can be used to sort of give us a threshold for whether or not the data is likely to be visually distinguishable. And as you can sort of see, as we increase the compression parameter, which means we're going toward more conservative levels of compression here, the compression ratio is slowly going to be decreasing towards uncompressed data, and the DSSM will be increasing towards 1 as we would expect. That's just one of the few metrics that we've identified as being useful for determining when our data is optimally compressed. So there's also some others, the Pearson correlation coefficient, spatial relative error, Kolmogorov superior p-value, and potentially the real information content. But which ones you might want to use are going to be dependent on the particular application, I guess. Now, trying to find the optimal level of compression for all of this data is kind of a brute force process that requires a lot of computing power and a lot of spatial storage. So what we kind of do is each of these columns represents one climate variable, and as we compress the data very aggressively, starting with a ZFP P6 parameter, we end up with a data set that's very small, represented by the size of that circle. And as we increase the compression parameter, we're moving towards higher data sizes, but also higher DSSIM values. So at some point, we pass a point where our data is across one of the thresholds we determined as being optimally compressed. And we take the smallest data set at that level that we can. And that's what we term as being our optimally compressed data set. We repeat this for all the climate variables and each time slice of all the climate variables. So again, very computationally consuming. And we do this for thousands of different variables and large volumes of data. So again, to ensure the highest level of compression, we need to kind of apply this to every different algorithm or every different compression variable and every different time step, and try several different compression algorithms and parameters to try and make sure we're getting the best possible level of compression. So what we want to do is create a statistical model that takes in data or some derived quantities of the data that we compute and use that to predict the optimal compression settings. So we use this as a baseline against which compression could be further tweaked if the scientists determine that those predictions are not quite sufficient. To compute all these metrics on this large quantity of data, we developed a Python package called LDCPy, which allows us to calculate not only those 5 metrics I described earlier, but also other derived quantities of the data quickly. It's parallelized using Task and is also designed to be interoperable with the Pangeo software ecosystem that geospatial that's used for the geospatial software stack. And it's all supports data sets in several different formats and also allows us to quickly add new types of analyses that we can perform on our data and compute new derived quantities. Using LDCPy, we're able to get an idea of what climate variables are able to be optimally compressed with what compression parameters. So here for each row, we have a different climate variable and we've compressed it to find the optimal compression parameter for each of these time steps of each of these variables. And for some of these, we see that there's not very much spread, like some of these snow or rain variables, but for some of these, there can be quite a broad spread in how much you can compress the data. So we don't want to just do something naive, like take the most conservative compression level. So what we want to do is create a statistical model that allows us to match the climate variables and time steps with an appropriate compression algorithm. And this will allow us to bypass that step of kind of taking that brute force approach to computing the optimal compression algorithm. So we can use that same brute force method to obtain labels for our data and then train this model to predict future optimal compression settings for either pre-existing climate variables that we've trained on or entirely new climate variables. And this is really sort of ongoing work. So I'll give you an idea of a few of the kind of initial results we have. We use both explicit and implicit feature models that we're modeling on. So in this case, we're using a random forest model that allows us to compute some derived quantities on the data, such as contrast variances, first differences, measures of data set information, to predict the optimal compression levels and give us an idea of how important those variables are in the resulting model. And we also use implicit feature models. In this case, we're looking at convolutional neural nets that that are designed to capture regularities in image data, and we're applying them to the spatial matrix of data values. And our early results indicate that using these basic statistical learning methods, we get kind of mixed results. As you might imagine, if we're predicting on a new time slice of a variable that we've previously seen, our accuracy is going to be a lot better than if we're predicting on a time slice of an entirely new variable that's not been included in the training data set. And this doesn't mean that this is entirely a useless model. It means that the model might be best for predicting optimal compression settings of a variable at a different time range or a different ensemble or something like that. But one of the major issues we run into when doing this is that it's hard to discern what new features we might add to improve the model further. And we're also not really able to increase the number of variables we have even more. So we can't really cover the feature space of possible variables any more than we already have. So what we're kind of looking at doing now is looking at a more local spatial approach where we look at local features of the data and make predictions in each region of the data and sort of average those all together to come up with a final value for our optimal compression parameter. We're working on parallelizing the code because depending on the particular setup we have to train a large number of models. And ultimately, we're trying to predict not only what is the optimal compression parameter, but what compression algorithm would be best to use before computing what the optimal compression parameter is. So that's another step that we have to take still. So that's all I've got for you today. Thank you.
So one of the stumbling blocks for me for using lossy compression is in the past, the inability to handle masked data where you have special values that need to be preserved precisely. Do you have ways around that now?
We don't really have ways around dealing with masked data at this time. Yeah, it's something that we're working on, but not yet. Thank you.
All right. Up next is going to be Tegan King and Michael Levy. So just come on up.
Okay. All right. Well, thank you. So Mike and I are going to be chatting with you all today about CSM Unified Post-Processing and Diagnostics, or CUPID. So right off the bat, I just want to acknowledge that there have been a pretty wide amount of people that have been involved in this work. So we have folks from all of these different groups. I've also italicized here the names of people who've contributed code directly into CUPID. So I just wanted to say thank you for everyone who's been involved in this effort and that it is a very collaborative effort. So as a little bit of background, and information on why ESDS, or the Earth System Data Science Initiative, is involved in CSM diagnostics is that CSM users were starting to hit the limits of what NCL-based analysis could handle. And so as there were some challenges coming up as NCL was no longer being developed, we started to recognize that there would be an advantage to everyone replacing NCL with the same product. And then the ESTS initiative kind of helped to find a solution for the community. So that was the Pangeo stack. And then we were recognizing that there were still a number of different independent efforts that were being used for analyzing CSM output. For instance, we had the Atmospheric Diagnostic Framework, or ADF, NB Squid in the ocean section, and a number of different one-off notebooks that individuals were writing. And we really wanted to build a common framework to address all of the kind of scattered efforts that we were seeing. So that led us to CUPID, or the CSM Unified Post-Processing and Diagnostics effort. So our vision is that CUPID is a one-stop shop that enables and integrates time series file generation, data standardization, diagnostics, and metrics from all CSM components. We're really hoping to focus on simplifying the user experience in order to run diagnostics and call post-processing tools directly from CUPID. We also want to be sure to run all component diagnostics from the same tool rather than from multiple different tools so that we avoid having single points of failure. And that we want to be able to run either directly as part of the same workflow or independently in order to make that easier for users to run in either situation. And lastly, we focus on sharing Python code and a standard Conda environment across all components to have a reproducible diagnostics that we're creating. So this is our timeline that we have had over the last bit of time. So in November, we met with different CGD sections to gather interest in CUPID. And in December, we sort of kicked off this effort with the various people involved in it. So the orange boxes show sort of the things that we have done, and then the blue boxes are where we are going towards. And this effort is kind of happening alongside CSM3 development efforts, as well as the CSM3 release, the CMIP PI runs, and the DEC experiments. So we're currently kind of at that aqua box of key metrics for CSM3 development. We have a current deployment that is available that includes a common environment, documentation, packages from all working groups, and a repository that we're using to gather feedback. And then you can see the blue boxes here, kind of the directions that we're hoping to go in the near future. So this is our GitHub repository. This is set up with some different projects and issues that we have to keep track of the work that we're doing for this project. Feel free to check it out. And then if you are interested in setting up CUPID in order to contribute to the repository or to run CUPID, you can do these simple steps of cloning the repository and then bringing in some externals. We also have two different CUPID environments. So we first would encourage you to create the dev environment, or CUPID dev, and that's the environment where we run all of the notebooks from. And so that our Plumer and some other bits of the framework kind of rely on the features that are in this dev environment. And then we also have a CUPID analysis environment. So all of the individual notebooks are run in CUPID analysis. So we have that environment that works for running all of our notebooks, and we really wanted that cohesive environment. If you want to actually run CUPID, we have an example that's provided in the repository. So you can change directories to that example coupled model directory, and then run the single command of CUPID run, and that will run all of the notebooks in the configuration file. And then if you want to build a website to look at the output, we have a command CUPID build that will then build a Jupyter book where you can look at the output. So we're trying to really keep this pretty simple for the user to have a nice experience with CUPID. If you want to run CUPID on any new cases or adjust your configuration file at all, you can modify the configuration file and then run those same two commands in order to run your new case. So currently, we have a mechanism for running notebooks in parallel, and Mike is going to dive into that a little bit more. We also have a time series file generation capability, and then we have examples for most of our components. We have some command line arguments, so we have options for time series or for running particular component notebooks and not others. we have our common environment that you run all of the notebooks in. And then we also have documentation on both contributing to Cupid or on just running Cupid. And then we also have some tips and tricks for running on NCAR machines that are in that documentation. So if you want to check out the slides, we have this link that points there. A few items that are coming soon are we're hoping to provide some key metrics for CSM3 development runs. So that is in progress right now. We also are hoping to be able to run Python scripts in addition to Jupyter Notebooks. We would also like to be able to run on machines in addition to Derecho and Casper. And then we're also currently working with a summer intern on running Cupid as part of the CSM workflow. And then lastly, we're working on running notebooks that import other diagnostic packages such as ILAM. And then I'm going to hand it over to Mike for the second half of this.
So there were three things that Tegan mentioned that we wanted to go into more detail on. One was this idea of if you don't just want to run our coupled model example, then you can edit a config.yaml file. Now I'll walk through like what we mean by like what changes you really need to make. And then two of the things that we have listed as like check marks on our where are we now? We're not really happy with the implementation of, so I thought I'd show what we've done and talk about what we actually want instead. So for the config YAML, it's a pretty long file that's broken up into a lot of sections, and we've highlighted with circles and the stuff that you probably need to change if you just take like an existing file from one of our examples. So data sources, this is telling us like this S name is used in a directory name where all of the output is created, and so you might want to give it a name that's more relevant to your example. The run directory and the NV path route kind of tell it where to run and where to find the notebooks, and those should probably stay fixed. For the configuration for the computation, this is where we say by default, run all the notebooks in the Cupid analysis environment. And we'd really like for diagnostics that will be shared as much as possible, we'd like to keep things running in Cupid analysis. If you have notebooks that use packages that aren't available, like talk to us and we can expand Cupid analysis. And if there are cases where you really just can't use this environment, you can specify like, oh, for this notebook, run over here instead. But we're trying to minimize the number of environments we want people to use. There's a section for global parameters that get passed to all notebooks. So for our coupled model example, we have output on Glade campaign, and we actually have an open PR that's working towards taking kind of hard-coded Glade paths out of things, but that was being done by some students last semester who are on summer break now, and so we're not sure when. So a lot of the stuff we're showing now really requires being on Derecho, but we're hoping to get into supporting generic machines soon. There's a time series block where you specify how you want to run the time series, and I'll talk more about what's actually being run. But the case name gets used for recognizing output from the file and for creating new file names for the time series files. And then under time series for each component, you can specify what variables you actually want time series out of, or time series files generated for. There's a compute notebook section that talks about what notebooks you really want to run. Again, this is broken up by component. And so in the coupled model, we have an atmosphere notebook called ADF Quick Run, and you'll probably want to change this with the notebooks you want to run. And then each individual notebook can have more parameters passed in from Cupid via this config file. And so you might want to change what's in the parameter groups as well. And you can think of those as just, these are inputs that are going to be passed to my notebook. And then there's a section for generating the JupyterBook HTML output. I should mention that these images aren't in our web documentation yet, but we'll get them included in the documentation as soon as we can. This is the kind of thing that we really want to share. Right. So Tegan mentioned that we support parallel processing. Right now, the way we do that is that we ask users to just request however much of their computer or that they want to use. And then internally, we use a Dask local cluster. And the benefit of this is that it's portable across machines. Like it doesn't matter what queue manager you're using. If you know how to request resources, then you give them to Dask and the local cluster uses them. The big downside is that it requires running notebooks sequentially, and not all of your notebooks need to use all the resources. So there's a lot of idle time. Like in our coupled model example, I think the ocean and maybe the ice use the parallelization, but the land and atmosphere don't. But you're still running those on this big part of the machine. So ideally, we'll be able to couple this with the CSM machine, the CCS config, and just have information on what machine am I running Cupid on? Like what is a queuing system? How do I get into the queue? And then we can pass that through Cupid. Then each notebook can just call the right Dask cluster if you want to be running in parallel. We have time series file generation. And so when we started the Cupid project, there were like 3 different options available for generating time series files, and none of them worked in all cases. So there's an ADF library that had one set of edge cases. There was something in the CSM post-processing, but I think it only ran on Cheyenne, and then Dave Valley might have gotten it running on Casper, but it wasn't portable to other machines. And Gary Strand wrote like a set of bash scripts that called NCR cat or called NCO commands under the hood, and like they all have their own quirks. And so what we really want, so what we did is we just copied the ADF one. It worked in enough of the cases to be useful for the examples we're providing. But what we really want is an external tool that can work. PyReshaper is what CSM post-processing used, and it would be great, except it hasn't been updated in 3 years. And so like we need something that's like PyReshaper, but still maintained, preferably by somebody who's not me. So just to summarize, like we're working on this portable and accessible CSM post-processing diagnostic feedback, where we're open to feedback, suggestions, testers, contributors. There is a development version available. And if you download these slides, like after the fact, that the next few slides kind of just show screenshots from web pages, but we're not going to take the time to go through them. So thank you.
Thanks. I'm wondering if any or most of this or some of it will be, you think it'll be operational for CMIP7 processing?
Yeah, we're hoping that this will be ready by CMIP7.
I was wondering what you think about for the time series generation. It would be cool to incorporate the option to do lossy compression on the data as it was written to time series.
Yeah.
You'd be, yeah.
Yeah, that would be cool. I think is Brian in the room? Like, so if you're really going to work on time series, that's a suggestion for you. But oh, yeah, yeah.
Probably already asked you this before, but for the Cupid analysis, is there any plans for the relationship between that Cupid analysis environment and like the NPL environment that Sizzle provides? Like, is there desire to merge them, to keep them separate?
I think if all the Cupid notebooks run in NPL, we should use NPL, although and just point people to the Sizzle GitHub repository where you can download the environment file to install NPL on other machines. If we do need to keep them separate, we're going to talk to Sizzle about maybe providing Cupid analysis on the Conda installations, like on the Conda modules for their supercomputers.
One thing I've noticed is that you have the NPL environment loaded, you can't build CESM.
Yeah. Yeah. So yeah. Yeah. Yeah.
All right, so we're getting to the end. The last talk will be by Jesse Nussbaumer. And if you have additional questions or comments, don't forget to put them in the Slido And those will be discussed tomorrow at the closing of the workshop. And I'll try to put the link in the chat in case you guys don't have it.
Hi all, thanks for making it to the end. Yeah, so my name's Jesse. I'm a software engineer here at CGD with AMP. And I'm here to talk about recent ADF developments and collaboration with Cupid. And I kind of saw this talk as a way of sort of like lessons we've learned from the ADF and how that would relate to Cupid. So like any prestige movie, I'm going to make you sit through the credits first. And I really want to give point out Justin Richling. He's the core developer of the ADF, and he should have given this talk here, but you know, he had family stuff come up, couldn't make it. I mean, yeah, he's fine. It's just the funeral that he has. It sounds really bad. It's someone's not really. Yeah. Anyways, let's just move on. So other people who seriously contributed have been Danny Coleman and then Brian Medeiros. They've kind of been the people who have done a lot of the core development, but it hasn't been just them. There's a whole host of people, which I tried to list here. And actually every single person here has contributed something to like the ADF repo. That can be issue, documentation, PR, whatever. So yeah, why does ADF exist? And it exists because of the old AMWG diagnostics. And since the software talk, it kind of got me thinking of what does it mean for software to be successful? Or what does this mean for software to be good? Because, so what the AMWG is essentially this program, which you could take in, provide CAM data, it would ingest it, do a bunch of diagnostic plots and analysis, and then put it on a website. And from a modern standpoint, you could argue it's not super well designed. It's basically a giant shell script that's calling thousands and thousands of lines of NCL. And you know, even if NCL wasn't being deprecated, it wasn't the easiest thing to add new features in or to maintain it. So one argument, you know, that's the negative. But on the other hand, I would argue it's incredibly successful. The first kind of usage I was able to find was from 2001, and it was still being used by scientists in 2023. So that's like over 20 years of production level usage by scientists. And so, I mean, I'm writing code that will not be used 20 years from now. So, so clearly what we needed was a replacement. We need something that was clearly providing what the AMWG diagnostics was providing, but trying to use more modern software engineering techniques to hopefully make it more maintainable long-term. So that's basically what the ADF is. Yeah, there's always a debate about what the A means, but here I wrote AMWG, sometimes the atmosphere. But yeah, essentially it's a Python-based replacement, you know, the whole pivot to Python, which does the same thing. It produces a bunch of plots and then puts them on a website. And there's an example of the website. And, you know, we try to use, you know, the Pangeo stack and supported tools like X-Ray and also more modern software engineering practices like unit testing, object-oriented programming, etc. And it's in production now, in the sense that, you know, AMP is using it to validate and to examine our current simulations. And this is, I pulled this from a real, you know, coupled eval 3 simulation, you know, the classic BE23 alpha 17 F BLT 1850 NE32 Jesus. Okay, well, anyways, that one, it's my favorite. And but, you know, the way we designed it is essentially kind of all these classes of plots. You know, you have like lat long, polar projections, vector maps, Taylor diagrams, tables up at the top, and which I can't do anymore. Well, there we go. And then zonal and meridional maps. So, yeah, so this is what's being used now. However, these kind of already existed a few years. Exist for a while, and like any talk, I have to emphasize that we have been doing stuff in the meantime, and by again we mostly Justin, Danny, and Brian. So new features, we've gotten a lot of help. We've kind of started being involved with ACOM, the atmospheric chemistry lab in at NCAR, and you know things they care about. I don't know why that O is there, well, whatever. One of the things they care about is high top cam, whack them like the stratosphere. And so we put a lot of effort putting in new plots related to the UTLS. For example, you don't really know what these are, but you know, the quasi QBO tape recorder, which shows how moisture is being transported into the stratosphere. tropopause cold temperature, and then the circulation diagnostic, which is the transform Eulerian mean. I would say there's two key takeaways here from the software engineering standpoint. One is Justin did a lot of these and he got a lot of pressure because he could be told, I want a plot that looks, by year, by height, and he would make that in Python, but then they'd be like, no, I want it to exactly match the plot I made in MATLAB through color and like the layout and everything. And so he would end up spending days getting it to, go from whatever, Barbie supercar pink to Barbie Malibu house pink, because that's the color that the scientist wanted. And I don't think that's a good use of his time. Like, as long as the numbers are the same, we shouldn't fight over that too much. The other key is, for the circulation diagnostic, I think sometimes we think of diagnostics as kind of being computationally straightforward. Like, you're just averaging and then you're just like plotting it over some, dimension or some slice. But for the circulation calculation, it's actually you're doing calculus, right? You're doing derivatives, you're calculating gradients. These are not trivial computations. And especially one thing I don't have here is, we're reading in the CBDP, which, Adam worked on. They're doing things like EOFs and spectral analysis, and none of those are always just, they're not computationally trivial. Again, just because ACOM has been supporting us a lot, just give a shout out. We have new plots related to things like carbon monoxide. I'm sure everyone's favorite in-house gas. We have, and then ozone. And I do like to show this plot because this is actually comparing cam run to ozone sondes that are launched literally here in Boulder. And look at the error bars of the observations are so giant that every model run matches it. So good job, us. So those are new plots. I also want to talk about something that Danny's been working on, which is bringing in the MDTF. And so, sure, as you've been here the past few days, there's all sorts of diagnostics packages out there, right? Obviously, we're trying to come into Cupid. We have the ADF. The ADF, we have CVDP, CVDP-LE, but then there's like the E3SM diagnostics and so on. And one of them that's provided by NOAA is the MDTF, the Model Diagnostics Task Force. And what it really specializes in is in diagnostics that are specifically focused on specific climate processes or modes of variability. So things like MJO, storm tracks and Rossby waves. I guess if I want Rich Neal to leave me alone, there's a thing there. And again, we could reinvent all of this, but it's much better to just try to bring it in. Which we've been able to do in the ADF. And if we can do it in the ADF, that basically means we can also do it in Cupid, right? At a bare minimum, Cupid could call the ADF, they could call MDTF. So, which is really exciting. So just, Mike and Tegan kind of already covered this, but, in terms of ADF coupling with Cupid, we have that basic notebook. We have, we pulled out the time series functionality from ADF, and so now every component can theoretically use it. Future efforts, ADF was really designed to not be run as a notebook. It was designed to be run as a script, which Cupid folks are working on. So hopefully when that happens, we'll be able to provide full ADF functionality. There's also additional work to pull out other ADF internal routines that don't really need to live in the ADF. So things like climatology calculations, and make them available to everyone. Feature design plan. So I have to admit, if you're talented like me, you can write bad code in any paradigm. And when I first started this off, I hadn't done much object-oriented programming, so I was really excited about things like inheritance. So I went kind of crazy on objects inheriting objects. And so for me, I was like, oh, this makes total sense. But as soon as people actually started using it, it became really hard to find. And so, for example, like everything is inheriting from something else and became difficult to use. And so one of our design plans has been to actually make objects independent. And so if they do it, if they are inheriting from something, it's because there's a really good reason to. And otherwise, internally, the ADF should only, objects should just instantiate other objects. Of course, general, we definitely want to add more unit testing. We want to implement more parallelism, mostly through Dask. And again, in terms of coupling with Cupid, one of the things in the end, we really want Cupid to kind of control a lot of the high level stuff, like where's my model data? What grid is it on? All that. And so and then just pass that to the ADF when need be. But that involves modifying the ADF to be able to accept like a Python dictionary instead of a YAML file. And then the same goes with as Mike pointed out, the same thing goes with the actual computing environment. Like Cupid should just tell the ADF, this is the number of processors you have and so on. So here's the part, I thought it was the end of the day and we're all stared at us. So I thought, now is the time I would give my opinions on what Cupid needs with my experience from the ADF. So the first one, I'm going to be honest, Cupid's going to have a hard time succeeding if it doesn't have more than like a 0.2 FTE or whatever. And that's not a slam on Mike or Tegan or them. They've been doing incredible work. It's just, as we fell in this in the ADF. When you start off something like with an open text editor, it starts off really fast. You're doing all this easy stuff, but sooner or later, the system gets complicated. It becomes harder to work with. And if you don't have someone working on it for a significant portion of time, it can get bogged down. Hackathons and interns aren't going to save us. I have mixed feelings on hackathons. In some ways I love them, but I also sometimes they're marketed weird because we always say it as like, oh, I'm giving you this opportunity to do this hackathon. But in reality, a lot of times it's, hey, I'm asking you to do work for me so then I can develop stuff and not pay you. And that's needed. But the problem is, we're all time limited. And what hackathons need is time. And we found with the ADF that even if people really wanted their stuff in there, unless they had time to do it, one of us had to get directly involved, which of course meant we had to spend more than just a small fraction of our time helping it. And interns can do incredible work, but their job here is to learn, right? To be educated. And so unless we're teaching them, cynicism and burnout, we probably shouldn't, enforce giving really hard projects to them, right? We should give something that's interesting. So, one other thing that's a real trap we found with the ADF and could be a trap for Cupid is basically feature creep. What's hard about this is if you design it well, right, the framework should be modular and extensible. So it's really easy to add stuff in. But the problem is the more you add, the more difficult it can be, especially when you have questions of like, who owns the new diagnostic that was added? Who's going to test the thing that was added? Who's going to do code review on the thing that was added? Who's going to help with the performance? And it's really hard to say no, right? Because you want to be supported. So you want everyone's diagnostic. But you can wind up with diagnostics that just aren't used that often. And we ran into that, sorry, you're all stuck here. So we have this problem with CAM output, right? We output like, I don't know, something like 250 variables by default. I'm pretty confident that 100 of them almost no one ever looks at. And so, but the problem is at the time, someone's like, oh, it's super easy to just add this output field. I'll just do it. And at the time, maybe it made sense, but they left or, that research project stopped happening and it's just now filling up disk space. And so I have the same general fear for diagnostics. There might be a reason now for a particular diagnostic, but will someone look at it 10 years from now? Yeah, and then high resolution is just going to be a problem. So it's not like it's technologically infeasible. Like we have, we have parallelism, we can make things scale, but I actually know for a fact right now there's things in both ADF and Cupid that do not scale well. And again, they can be fixed, but if we don't have someone spending time on it, it could be one of those things that as soon as you try to give it quarter degree model input or higher, it just seg faults. And so, and there's also too with, the problem with the packages we use, even you get a high enough resolution, even like rendering plots becomes really hard. And so, again, it's solvable, but I think it's just to that top point. If someone's not spending a large amount of time on it, it'll be really hard to do. So yeah. All right. On that happy note, that's all I have. So thank you.
Yeah, it was a great talk. Yeah, it's good to wake up people. No, it was great. I feel you have a really good point that we need to have more than 0.2 FTE to have this, but also we need not only to build it, but we need to think about maintaining it in the future. Then it's not like more, even for the future, it really need really a full FT, or I don't know how much
Yeah.
you think we need. And I think something that when I was looking that we have more and more set of diagnostic, what would be really nice is that I didn't know now the MDTF was running out from the ADF.
Okay, well, technically the PR is still open.
Yeah, but it's going to be, it would be nice to have a set of variable. At some point, we can have a nameless variable in CAM to call, to make sure that when you want to run a set of variable, you ask for this variable as an output. When you want to set of diagnostic, you are outputting the right variable. Then it's something to.
Yeah, I agree. So,
Yeah.
Thanks, Cecile.
Hey, great talk. Thanks. I'm wondering if we're preaching to the choir here or whether some, funding agency was in this room. Thanks for bringing up the point about the funding. I'm glad I wasn't the only one to say it. One thing you kind of glossed over was the difficulty of moving from the FE DACOR to the SE DACOR.
Yeah.
And, I know that a lot of effort had to be put in to get the SE DACOR to do some of the, longitude averaged fields and stuff. How about the regionally refined grids? Are those able to be used in this?
I mean, again, my understanding is in theory, yes, because I know like Adam Harrington is running it and making plots, so somehow it must be doable. But yeah, one thing I didn't bring up here is we talked about like time series, but there's also unclear how we're doing regridding in general, because there's like, a bunch of different tools and in the ADF, we're kind of using this like made up bilinear thing. But yeah, I think there's just a bigger discussion there about like, if we could collectively come up with, using ESMF or something to do our regridding, and that can handle unstructured as well as structured. And then, then hopefully we could even look at regionally refined and everything. But right now, the ADF can only do structured grids. And so you have to do the regridding beforehand. Yeah, which is a flaw.
Yeah, great talk. You woke us up. That's
Thanks.
great. So kind of going on to that last question, because I think everything you're doing is based on X-array, and there's UX array now that does unstructured grids, which it might do variable grids. I'm not sure. Variable resolution grids.
Yeah. I mean,
have you looked at that, or where is it at?
Yeah, we definitely want to. Obviously, ADF started before UX-ray existed, so it's X-ray. But yeah, we definitely want to do. We definitely want to implement UX-ray, and one of the things we thought about in the ADF world is kind of making that decision for you, like in the sense of like we can look up and see, are you using a spectral element grid?
Oh, right.
We just use UX-array.
Yeah.
If it's a FB grid, UX-array.
Right.
Yeah, there is a question about like how it. So in the ADF, there's a lot of plotting, as I mentioned, like people want plots in a really specific design. And so you have to use like matplotlib and other packages to set up that plot. And it's unclear how that interacts with UX arrays data set. There's also the question, which is kind of more of a user. We don't know what the user wants in the sense of UX array would work best if we kept everything unstructured. We went straight from the model to the plots. But there's a question of, do people want Cupid or whatever to do to regrid things into structured grids? Like basically, how are we storing the data? Are we going to store it always unstructured, or do we want to translate it into structured and store it that way? And that's not, I don't have the answer to that. So,
there's a bunch of questions that a lot of them are science.
But we definitely want to use UX. Yeah, I mean, again, we need some way to manage unstructured grids, because that's going to be our default grid set on. So,
Exactly.
And UX array is definitely one of them.
Exactly. Okay. So, UX array does extend X array. You talked about object oriented. It does extend it, and so I think it might just work for structured grids. I'm not definite here, but there are probably going to be choices too that still have to be made.
It's in theory, matplotlib can take an X-array data structure, so I don't see a reason why it couldn't take a UX-array data structure. But just because theoretically that works, I don't know if it works.
Exactly.
So we definitely want to explore it. It would be an awesome tool if we could use it.
Right. Okay. Cool. And then the last question is, I appreciate you talking about design, as well as Alper talking about design and thinking about design. And you showed some diagrams, and I was wondering if you if you, the diagrams that you showed, or that's something that you developed or that you're using now, or what's the process you had for your what was the design process? You know, do you have a bunch of UML diagrams that you have that you've been building and you're adding to, or, you know, just tell me about
Yep.
that.
So the first answer to that is no. This I created for the last ADF talk 2 years ago, and it's just a PowerPoint slide.
Okay.
The ADF was not what Alper was envisioning, in the sense of it's not like we started off thinking we're going to do the design first, we're going to flesh it out, and then we're going to build the software. It was done in the way of like, actually at the time we weren't sure what was going to be the MWG replacement, so we built it as just this like quick straw man, and then somehow that got selected, and so then we just kind of kept adding on. So it was always this. The way I've always heard it is we never made strategic decisions. We just kept making tactical decisions about adding things on.
Short term rather than long term.
It's actually part of the reason. I mean, a little hard myself. It's part of the reason why everything is just inheriting, because I had a class and I had to add something on, so I I made it inherit. Thinking about how to actually organize it well, and so So, anyways, yes, that's
okay.
I would. Yeah, again, part of this discussion was it would be good to actually think about the design of the ADF and design in a way that's
okay.
at least easier to read.
Cool. Awesome. Thank you. Okay. I see you.
Thanks. Jesse will be happy to answer questions like in the coffee break. So let's thank all the speakers for this session. Please put your questions and comments on the Slido, the links in the chat. I hope to see many of you in Sanita's Brewery tonight at 6 to 8 p.m. for the icebreaker. And Mike, what else? Do we have any other announcements? What? Sorry.
And just thank the AV support in the back. Yeah.